Okay, let's get started. We're going to continue the main memory lectures. It's a concept I cannot overemphasize. Whatever design you will deal with in the future, you will deal with main memory, as you know. That's true for data centers also. Today, actually, a big cost of the data center, it goes to main memory. Not really the processor part of the server, but really the memory. People really need more memory. They buy more memory. They pay a lot for it, actually. And that's going to increase. That's not going to reduce. That's one of the reasons why this is really important. So we will cover more of DRAM operation, talk about memory control, and hopefully get to memory latency. Because as you know, latency is not improving as fast as other things. But this is a very quick, high-level summary of last lecture. We talked about enabling high-bandwidth memories. So hopefully you remember that. Main memory system, we gave a broad perspective, and we talked about DRAM fundamentals and operation. Okay? We talked about a lot of trends in the main memory system. Today, we'll continue the DRAM operation and switch to DRAM controllers, how to control this beast. And whenever you're designing some system, you need controllers, and memory is nothing different. But memory is important because you want to access it with low latency and high bandwidth, and if your controller is not good enough, then you have a problem, right? Actually, control is important. Like this thing needs a controller also, right? Everything over here needs a controller, and they need to work, but not necessarily with the same design constraints. And we will also talk about simulation, actually, at some point during this lecture, and why it's important, just to give you an idea of how we actually evaluate some different techniques. Actually, it's more of an evaluation methodology, like part of the lecture. Okay, but before I continue, are you guys aware that your lab 1 is out? You've seen the email? Okay. I think it's going to be a fun lab. Basically, you'll add a data cache to a pipeline processor, which is good. Have you guys done a pipeline processor before? Yes? In Verilog? RTL? Okay, maybe one of you. Okay, well, we'll give you the pipeline processor in this case, so you'll start with that, and you'll implement the data cache. And certainly there are some requirements in the data cache, but there's a lot of extra credit opportunity also. So if you finish it early, do the extra credits too. I think you can get 100% additional extra credit. And if you actually do a really good job, I'll give you more. Basically, the goal is to learn. The goal is not to really be crazy about grades. That's why we give you a lot of extra credit opportunity in this course. Okay, and it should be a lot of fun. And it's due 18th of October at the moment, which is 2 weeks from now. Okay, with that aside, hopefully you're doing homework 1 also, which is due soon. And we've covered almost all of the topics related to homework 1. There's one on virtual memory, which I'm not sure if we will cover, but you can figure it out on your own. You should really know virtual memory coming to this course, I think. Okay. Okay, we'll continue this. Basically, these are some readings, some of which we're going to cover. You should definitely look at these. These are required, and we'll cover this also today. So this is where we left off. Basically, I had given you the DRAM subsystem organization from the bottom up. Now we're going to do it top down. In the end, we ended up with something like this, right? It's a 5-dimensional organization channel, and then with the channel, you have the DIMMs connected to the channel, and you have the DRAM banks. And with each DIMM, you have a rank. By the way, does this bother you also? I think there is some flickering going on. Can you guys see it from there? No? You can? Okay. Who is bothered by the flickering? Not bothered, maybe. Bothered, maybe though. Maybe this is the problem with the HDMI connection, because I can see it right now. I didn't see it in the past. Anyway, let's continue. Is that a problem? Okay. Yeah, I think that might be the, maybe you can. I always have a problem with the HDMI connection, so this is a good lecture about interfaces also. Think about why we have so many interfaces like this. And they're all different interfaces. We'll talk about the memory interface more. Sorry for that mishap. We're back. There's something, I think this is a known problem. We should never exercise known problems. There's something that happens with my computer's HDMI connection, and whenever I connect to HDMI, something weird like this happens. I cannot pinpoint what it is, but either PowerPoint dies, or apparently my computer shuts itself off. OK, this is where we were. Hopefully it doesn't happen again. OK, yeah. Basically, we covered the 5-dimensional structure, and I recommended that you take a look at this paper. We'll cover some of that also. But you should be familiar with all of the concepts over here. You have a memory controller controlling a channel. A channel consists of multiple ranks. Each of the ranks consists of multiple banks, and each of the banks consists of a 2-dimensional array of cells, and you know how a cell operates. So we're going to go from the top down right now. Basically, we started this way. Now we'll do it the other way also. So if you look at a system, you basically have a processor and memory connected to it, right? And these are different channels. In fact, in Core i7, I think you have 3 channels, maybe more. In some more scalable processors, you need even more channels. And if you look at what's connected to each channel, basically these are different DIMMs, right? You could actually put more. And let's focus on one DIMM. If you break it down, you can see the ranks. You may have chips in the front and chips in the back, right? Those are different ranks of the DIMM. And you have this little thing over here, which is serial presence detect, that tells you information about what your memory is. This is what the memory controller reads to understand what the memory is. And you can actually store other things into the serial presence detect. There's some non-volatile memory in it. OK, so you can see the different ranks, as I mentioned before. This is, as you know from last lecture, rank is a collection of 8 chips that respond to the same command, same address, but give the different data. Right? OK, let's break down the rank. If you look at the rank, these are 2 different ranks. Basically, you can access only one rank at a given time. Even they share the data bus, as you can see over here, right? They share the address and command buses also. So only one rank can be active at a given time. When you break it down, you see the chips that we've discussed. Basically, multiple chips respond to the same command and same address with different pieces of the data, such that you can get 64 bits in an access. And if you break down the chip, this is what you see inside, right? Basically, you have 8 banks over here, and those banks share the data bus going out. But they can be accessed in parallel. So you can start one access in this bank, and then the next access in the other bank, in some other bank, in consecutive cycles. So you can overlap the latencies of the bank access. Now, you can break that down also. And this is what we got. This is what we started with. It's a 2-dimensional array of cells, right? Of course, I didn't show you exactly how big it is. And how big it is depends on the chip also. But this is an abstraction. But we have basically rows and a bunch of columns. And to access the column, for now, consider that a column is 8 bits. You basically need to supply a row address and a column address and get the 8 bits. Make sense? And for those 8 bits, those consist of smaller cells. So this is the other way of looking at it, coming from top down. We start from the bottom up. So you know hopefully how everything works over here in this system. And we're going to look at different ways of optimizing this. But let's take a look at an example of a cache block access in a modern system. So if you look at the physical memory address space, a cache block is a contiguous 64 bytes, assuming your cache block is 64 bytes. And this 64 bytes gets mapped to a single rank over here. But remember, one access gives you 64 bits, which means that you need to do 8 consecutive accesses to get the 64 bytes, as I mentioned before. So the first 64 bits comes from this locations. Remember, a rank gives you 64 bits, so you need the cache block actually gets mapped to all of these different ranks. The next 64 bits in the cache block comes from the next part. The next 64 bits comes from the next part. The next 64 bits comes from the next part, ... until you have all the 64 bytes, right? So you basically need to do 8 transfers over the memory bus. During the process, you read 8 columns sequentially from the different chips. So that's how it works. There's no magic, basically, in the end. I mean, this is very simple right now, hopefully, to everyone. But this takes time, of course, right? So let's take a look at the latency components of basic DRAM operation. And I didn't tell you all of the latency components. The first thing is the core or the CPU needs to ask the controller, I want this cache block, right? So there's some transfer time. So that starts all the way from the processor. So you need to access the caches, all of the levels of caches to figure out that you missed in the last level. At that point, the request goes to the memory controller, right? And then there is latency in the controller. So there's latency before the controller. It may be actually some other processors also could be asking, so there's buffering that happens. So that latency could be high. Even the first latency could be high, depending on how much contention you have on the chip. But there's also latency in the controller, because other things may be buffered in the controller, right? There might be queuing latencies and scheduling delays at the controller. And accesses are converted to basic commands. OK, I didn't do that. That's automatic. One could consider that this room is a robot. It has a life of its own. Basically, you have the controller latency, and controller needs to convert the access to basic commands. And this actually adds some overhead, as we will see also. In addition to queuing and scheduling delays, because some other request may be pending, and the bank may not be available, for example, or the bus may not be available, there's also some other overheads in DRAM. For example, there might be refresh, right? So you may need to wait for that. So all of that is lumped into controller latency over here. And then there's controller to DRAM transfer time to give the commands. So that's called the command latency. And then there's the DRAM bank latency, which is a large component, actually. And depending on what state you're in the bank and what you're accessing, this latency could be even larger. For example, if you have a row hit, you just need to send the column address, right? This is also called the column address strobe. I use slightly different terminology so that you get used to it. But DRAM is unfortunate that it has different terminology. But this CAS means simply a column address strobe. If the row is already open, meaning the row that you're trying to access is already in the row buffer, that's a row hit, you just need to send a column address command, a read or write, and that's fast. If the array is pre-charged and there's no row that's open in the bank that you're trying to access, you need to send the row address and the column address, so that takes a little bit longer. And if, in the worst case, there's some other row in the bank that you're trying to access, that's the row conflict case. I should have said conflict over there. Then you need to first pre-charge the array, send the row address, and send the column address. And each of these takes time, as we will also see later in this lecture. And you will see in your readings. And that's the worst case access. And this takes pretty long. OK. And we're not done yet. After that, the DRAM needs to send the data back to the controller. That takes some time. This is the bus latency, basically, however long it takes to send all of those 8 data bursts back into the controller. And after that, the controller needs to transfer it back to the core, right? So there may be delays associated with that also. And you can break this down also, because you need to send it to the cache, and then cache needs to send it back to the core. And if you have missed status handling registers, missed buffers, that takes some time also. But this is on chip, so hopefully this is much faster. OK. So that gives you an idea of the long latency to access main memory. Yes?
We haven't considered here, like, if we have a cache miss and we need to write back data to the memory.
Yeah, we have not even considered that. So we want to not right now, but I'll give this to you so that you can throw it at the person who's speaking. So in this case, yeah, this is basically for the load that's trying to access some data. It doesn't even consider something that it evicts. So there's some other latency over there. But the hope is that that's not on the critical path of this load's latency, meaning that you don't need to do that eviction first and then do this. You can do that in parallel. And that eviction is less critical because you don't need the data from that cache line. You can write it back when it's convenient, hopefully. OK, so we talked about multiple banks. Let's take a look at that. Basically, there are multiple ways of doing banking. And earlier I said that you could actually have you could actually have banks that can be operated in parallel. Well, if you have complete parallelism in the banks, meaning you have independent data buses, that's really called a channel in main memory, at least. You basically have 2 different channels, and you can operate them completely in parallel. If you have banks, for main memory at least, we say that you really have, for a bank, basically, you don't access it independently. They have a single address and command bus, and a single data bus. So they share those. So in main memory, we don't have completely independent banks. They always share the data buses, and address buses and command buses. But they still enable concurrent DRAM access, but concurrency is really overlapping of the bank access latency, right? It's not the complete overlap. And as we've seen, bits and address determine which bank and address it resides in, right? So multiple independent channels serve the same purpose, but they're even better because they have separate data buses, right? And separate command buses, separate everything, actually, separate controllers. So this gives you increased bus bandwidth. You don't transfer only 64 bits at a time, but also 264 bits because you have two different channels, right? OK. So actually, channels are better to have, but of course, they're more expensive because now you have more pins in the processor chip. So of course, enabling more concurrency requires reducing the bank conflicts you have and reducing these channel conflicts. And we've seen this earlier. And you can actually use similar methods to reducing the conflicts that you have in the banks and channels as we have used in the caches to reduce the cache set conflicts, right? And I'll give you one example of this. So how do you select and randomize bank and channel indices in the address? Well, usually people use lower order bits because there's more entropy that changes a lot depending on what you access. And also you could use randomizing hash functions, as we've discussed in caching. So the techniques, as you can see, apply to very different things. Not caching, but in this case, we're talking about channels. So this is a very quick example of how multiple banks can help. I should go here to see. But basically, you have the address bus and you have the data bus. And if you have a single bank or if you have bank conflicts, this is what you get, basically. You give the address, and you wait for the access, and you get the data. And then you can start the next access while you're getting the last data, the data from the previous access. So this is what happens when you have a bank conflict or a single bank. Accesses are serialized. Whereas if you have 4 banks over here, what you could do is you could pipeline the addresses. You could send one address every cycle, which means that the banks that receive the addresses start one access every cycle, and the data at some point comes out, and data comes out in a pipeline manner as well from the banks. So you overlap most of the access latency of these 4 accesses this way. So if you have enough banks, you could fully utilize your data bus, right? If you have enough banks, enough parallelism, of course, in your access stream such that you don't have bank conflicts. And we've seen this before with the Cray example that I mentioned earlier, right? Each bank access latency takes 11 cycles in Cray 1. If you have 16 banks, and if you're starting one access per cycle, you could saturate your data bus, which means that you're getting one data burst every cycle. Hopefully this is clear. Now, if you have channels, of course, then you have multiple data buses, so you could actually get multiple data items in a given cycle. So this is one example of address mapping in a single channel. Basically, if you have a single channel system with an 8-byte memory bus, and if you assume these parameters over here, you would see that we will have an address that looks like this. And these are 2 commonly used ways of interleaving data across banks. Assume that we have a single channel here at the moment. And once we have a channel, then we have the question of where to place the data, which channel to place the data. But let's take a look at the question which bank to place the data. So one common way of doing it is in using row interleaving. In this case, the consecutive rows of memory are in consecutive banks. Assume that we have 2 kilobyte rows, which means that the first 2 kilobytes are in this bank, the next 2 kilobytes are in this next bank, the next 2 kilobytes are in this bank, ... Basically, you interleave the rows across the banks. And this means that accesses to consecutive cache blocks are serviced in a pipeline manner because they're in the same row, right? Or you could do a finer grained interleaving, which is cache block interleaving. In this case, the consecutive cache blocks are in consecutive banks. First cache block, 64 bytes, is in bank 0. The next 64 bytes is in bank 1. The next 64 bytes is in bank 2, ... As opposed to first 2 kilobyte, right? In this case, access to consecutive cache blocks can be serviced in parallel in different banks. But the performance of these 2 actually are same if you don't have actually bank conflicts. Right? If you're accessing different cache blocks, then you will get the data. OK. Does that make sense? But this, of course, determines your bank conflict patterns. Right? Now you have 2 kilobytes over here. Now you have 64 bytes. Now, or your row buffer hit rate also is affected by this, right? Because what data is in your row is determined by this interleaving. Here you have consecutive 2 kilobyte blocks from physical memory space inside the row. Here you don't have consecutive 2 kilobytes. You have the 64 byte, and then the next one is probably 64 byte times the distance between the first 64 bytes and the next 64 bytes is 64 byte times the number of banks you have, right? Because you're really interleaving across the banks. Make sense? You can think about it. There's nothing magic over here. OK, so what a lot of memory controllers today do is to try to reduce bank conflicts as much as possible. So one example of what they do is they can randomize the address mapping so that bank conflicts are less likely by XORing some bits of the address. So this is one example. Oh, OK, let me go back over here. So this is the address mapping that you have with row interleaving. You need to select the bank bits such that 2 kilobyte chunks are in each bank. So you need to select the bank bits from here somewhere. And if you do cache block interleaving, bank bits needs to come from the lower bits of the address, clearly. But you could also randomize things so that you could you reduce the probability of bank conflicts, right? So one example over here is you take 3 bits over here and XOR it with some 3 bits that you potentially randomly select from some other part of the address. This is a very simple hash function, and it's a reversible hash function. You do need a reversible hash function, right? You don't need a complete. You cannot do a complete random mapping, which is different every different time, right? It has to be predictable. OK, so this is one example, and you could actually make this even more complicated, right? You can actually have a randomizing matrix that actually you can XOR it with the different hash function. And this paper this is a very early paper by Bob Rao that talks about how to reduce bank conflicts, and he actually goes into a lot of theory on how to do that. If you're interested, you can take a look at it, but you can see that it's a relatively old paper. But the reason they actually examined it at that time, actually throughout the 1980s, is really, again, because of supercomputers. So if you have a supercomputer, you need a lot of banks to sustain the memory parallelism that you generate because of large parallelism that you have in computation. And you need to minimize the bank conflicts so that you can sustain the data input to the computer. So what they did was they actually did a lot of sophisticated schemes to minimize those bank conflicts by looking at this hashing function. As opposed to looking at simple XORs like this, they looked at much more complicated hashing functions to minimize the conflicts. Because inevitably, if you have a lot of accesses to memory, and if you have a limited number of banks, you will have bank conflicts, right? And you want to minimize those bank conflicts as much as possible. OK, so this is an important topic. I'm not going to go through this in even more detail, but this becomes even more complicated if you have multiple channels, right? This is one example over here. Now, if you have even a single channel, you have a choice. Where do you place that channel bit? Is it the top bit? Is it somewhere over here? Is it somewhere over here? Is it somewhere over here? Do you do byte interleaving, for example? Which doesn't make a lot of sense, perhaps. But depending on your granularity of access and locality of access and the access patterns, some of these other ones make sense, right? So where are the consecutive cache blocks? You should be able to figure that out. That's not that hard. And you could do even more over here, right? So basically, you don't need to have consecutive columns over here. You could actually break those down as well. Basically, your channel bit can be anywhere. And the conflict patterns you get across channels and across banks depends on which bits you select. That's the takeaway. So who influences this? Clearly, memory controller does part of this mapping. But there's also some other influence that potentially can come from the higher levels of the software stack, which is the operating system. Right? If you look at the operating system can do virtual to physical page allocation. That's one of its functions in virtual memory. And if you look at the address, the virtual address, it looks like this, right? And what the operating system does is it translates that virtual address to a physical frame number. That's address translation. And the page offset remains the same in the address in that case, but this mapping can be changed, right? Now, clearly, this is assuming that you have a 4 kilobyte page in this case and a byte addressable memory. And if you look at this physical address from the point of view of what we've been looking at in DRAM, it looks like this, right? Which means that the operating system, assuming you choose the bank bits from here, the operating system can have an effect on which location it can place, which bank it can place a particular page in, right? Or if you have a channel bit over here, the operating system can have that effect as well, right? So the operating system can actually potentially affect these conflict patterns by doing this allocation well or wrong, or even even if it doesn't know about it, it may affect the allocation patterns, right? So that's the idea. So if, for example, if the operating system somehow figures out that these two processes should be isolated from each other, it can map them to different banks by choosing a proper virtual to physical allocation. For example, for this process, it can always allocate physical frames that have these 3 bits set to 0. It can allocate for another process physical frames that have these 3 bits set to 1. That way, it maps this particular process to bank 0 and this other process to bank 1. Make sense? That's simple. Well, I've said this already. So this is what I just said is called page coloring. You can think of these 3 bits giving you colors, 8 different colors. So you have 8 different banks. And the operating system, for different processes, can choose different colors to allocate data from, to allocate physical pages, physical frames to. And that influences which bank you're allocated in. And this way, it can minimize bank conflicts. It can minimize inter-application interference. We may cover that later on. It can minimize latency in the network, potentially, depending on how you do that allocation, because these address bits can be used for other things. For example, if you have a cache system, if you have a multi-core system where the cache is distributed across different cores, the operating system may have an influence in where each of the data block actually resides in that multi-core system. That's also true for a non-uniform memory access system. You have multiple processors, and the operating system may have influence. Actually, it does have influence on which processor's memory a particular block resides in. And by being aware of this mapping over here, this where the bank bits are where the bank bits are in the physical address, and maybe where the channel bits are, and maybe where some other bits are, it can actually make intelligent decisions. Make sense? Now I'm saying this is all nice and good, but the problem today is for this to work, for the operating system to make intelligent decisions, this address mapping at the bottom that I show you over here should be exposed to it, right? The operating system should know which bits in the physical address the memory controller is using to determine which bank should be accessed. If this information is not available to the operating system still has some influence, but it doesn't know. It cannot control which bank to place the data in. Unfortunately, in many of today's systems, the operating system is not given the information about what the memory controller does. So for example, I showed you something over here, right? This randomization function. The operating system should really know about this function if it wants to influence that address mapping of a virtual page to a particular bank. But if that function is not given to the operating system, then you have a problem, right? In most modern systems, that function is not given. You could potentially reverse engineer it. Actually, people have reverse engineered it and written papers and designed your operating system based on that, but that's kind of not so nice, right? So this is actually a really interesting direction, I think. How do you actually provide interfaces to the operating system such that it can do much more intelligent decisions about this allocation? This is not a solved problem at the moment, unfortunately, but there's a lot of control at that level. OK, we will see page coloring later on when we talk about shared caches in multi-core systems, because operating system actually has an influence on the conflict patterns that you get in shared caches as well, because a similar thing happens in shared cache indexing, right? Because the index of your cache comes from your physical address, and the operating system has influence on which bits of those physical address are allocated to which frames, right? And we will see that. The operating system actually can reduce the cache conflicts between two different processes by intelligently choosing physical page numbers and doing the page coloring that I just described, assigning some colors to one process and some other colors to another process. That way you can partition your cache. Just like we did partitioning right now. You can partition your banks across different processes. And clearly you can partition your channels, right? You can say, for this process, I'm going to allocate addresses from channel 0, assuming, let's assume that your channel bits are coming from here. And for other process, I'm going to allocate pages that are coming from channel 1. Of course, operating system has influence over this part of the address, right? If your channel bits are coming from here, well, you have no influence because this page offset remains unchanged during address translation. OK, good. Any questions? Yes? OK, there you go. The first use case.
When you talked about the memory banks, is one cache block, like 64 bytes, is that in one memory bank in the end?
So usually, yes. If we go over here, these are the two major interleaving schemes. And if you use either of these, yes, that's 2.
And I can only access 64 or 8 bytes at once because of the bus. So I have 8 cycles for one cache block. And then if I pipeline this again, is it again 8 times those 8 cycles?
Exactly. Exactly.
Oh, okay.
So for each cache block, you spend 8 cycles on the memory bus.
OK. Yeah, that was it.
At least in most modern systems, right? You could, of course, increase your memory bus size, but your cost increases that way.
And why don't I distribute one cache block over all those memory banks so that I have only 8 cycles of latency?
Well, the problem is the banks still share the data bus, right? So you cannot perfectly parallelize cache block access.
Yeah, but I can have one pipeline, and instead of 8 times 8 cycles.
Yeah. So, even if you do one bank, it's actually pipelined today.
Oh, because of the row
Because
buffer?
of the right, exactly, because of the row hit latency and the data burst.
OK.
Because of the page mode DRAM that we talked about last time.
OK, thanks.
So you can parallelize if you actually put it in different channels. So part of the cache block comes from this channel, part of the cache block comes from this other channel. Now you're completely parallel, right? So that's the multiple dependent channels that we talked about last time. They're not independent channels, but they're dependent channels. But the purpose of that is to increase the bandwidth that you get. Okay. OK, that's a good question, though. OK. OK, so there's a lot to be done on bank conflicts, and there's more on this. I'm not going to cover this. In fact, as I mentioned to you earlier, even a bank is not a full physical thing. The bank is actually divided into smaller subarrays internally to minimize latency. We will see that later on today. Just because the bit line that's spanning all these 32,000 rows in this case is just too long. So we actually divide into smaller subarrays, divide each bank into smaller subarrays. And maybe there are some conflict patterns that exist over here, too. So this paper talks about how to reduce bank conflicts and different ways of doing it. And we may cover it at some point. But let's move on right now with other memory control issues. OK, we talked about DRAM refresh. I'm not going to skip. I'm not going to spend a lot of time on this at this moment, at least. But you know that DRAM needs to be refreshed. And there are implications on performance. Right? One is DRAM bank is unavailable while refresh. This is an example of a bank conflict, except it's not coming from some other access. It's really coming from refresh. So how do you actually reduce that conflict? Well, I don't know. One way is reducing refreshes, as we've discussed, right? If you get rid of refreshes, you get rid of those conflicts also. And there's also an issue, long pause times. If you actually refresh all rows in burst at the same time, every 64 milliseconds, that's the refresh interval in today's systems. Actually, it's reduced to 32 milliseconds, I think, in LPDDR4. Is that correct, Hassan? Yes. OK, there you go. So if you refresh all rows in a burst every 64 milliseconds or every 32 milliseconds, the DRAM will be unavailable until refresh ends. Now, this makes no sense, of course, right? So this is called burst refresh. All rows are refreshed immediately, one after another. It used to be that old memory controllers used to do this, and people have figured out that this is better, distributed refresh, which means each row is refreshed at a different time, but every row is refreshed at a regular interval. So this is the pictorial view of it. So this is the burst refresh. Each pulse is a refresh cycle. So you refresh, whenever the refresh time comes, you refresh all the rows in burst. And then there's there's some amount of time. You don't need to refresh anything. But then your refresh time comes again, and you need to refresh all of the rows at the same time again. Now, this is not good for quality of service because for this duration, almost all of DRAM is unavailable. Whereas if you do the refresh in a distributed manner that looks like this, distribute each different rows refreshes at different times, you get a much more consistent performance, if you will. You still do the same number of refreshes, of course, right? You still need to refresh all the rows every 64 milliseconds. But when that refresh happens is different for each row. OK. So this is what's employed in modern memory controllers. So the question is always, how else can we reduce the effect of refresh on performance and energy? And we've seen an example of this and how difficult it is before. OK. So a radar paper you've been reading. But the refresh also, it's not only performance, but it's also energy consumption. And as we've seen, refresh rate limits DRAM density scaling. And I'm not going to go over this more in this lecture. Any questions? Have you guys done any of the readings so far? Yes, that's good. You read the radar paper? Some of you? Who read the radar paper? OK, cool. So you can tell me about the refresh. Maybe not right now. Did you like it? OK, cool. All right, let's talk more about memory control. So radar is one example of improving the existing memory controller design, right? How do you implement it? It's still in the works. But let's talk about memory controllers in general. And we've talked about several things. Regardless of whatever memory you design, long latency memories have similar characteristics that need to be controlled. Remember, I asked you the question, does flash require refresh? Even though it's non-volatile, it does require refresh also. So you need to control these characteristics. So the following discussion that we will have in this lecture about memory controller, we'll use DRAM as an example. But many scheduling and control issues are actually similar in different controllers. So if you actually know how to design one controller really well, you could potentially design some other controller really well also. Of course, you need to adapt to the different characteristics of different memories. So clearly, we are not going to be able to cover all of the different controllers in the world. But we will cover DRAM in a little bit more detail. But flash memory is important, and it has controllers also. And I'll give you glimpses as to how it can be controlled. And there are other emerging technologies which we will cover in a separate lecture. But we won't talk about the design of the controller in a lot of detail in those cases. Because a lot of the principles that we will describe today will apply to a lot of these different memories. So phase change memory, spin transfer, torque, MRAM. And these other technologies can place demands on the controller, other demands on the controller. That may be different. So this is one example. We're not going to cover this in detail, but this is a modern SSD controller. It's similar to DRAM controller, except they're flash memory specific, right? And they do much more. Error correction, garbage collection, page remapping, ... In fact, there's a little buffer manager over here. And you guys know what that buffer is? It's actually DRAM. There's a little DRAM chip over here, well, a DRAM buffer over here. And you need to have a DRAM controller inside a flash controller to make this work, because you have that DRAM to improve the performance of writes, for example. You can write it to DRAM. It's used for many things, actually. But one of the major things is to do the mapping of the logical pages to physical pages. So a flash controller actually does a lot of mapping of the data to ensure that long latencies are not experienced by the system. So, but if you want to learn more about it, you can take a look at the papers that are referenced over here. And this is a more modern view of the control. But this explicitly shows that you actually have a DRAM manager and buffers. And the controller, flash controller, is responsible for a lot of these things. So compression, for example, some controllers are encryption, scrambling of the data, and error correction. In flash memory, you need that error correction because otherwise your memory doesn't work, really. Most of the bits that you get out of flash memory are almost useless if you don't have error correction. That's the type of technology. In DRAM, it's becoming that way, as we've discussed earlier. But it's not at that point fully yet, although chips are incorporating ECC internally right now. So going forward, we may see similar parts in a DRAM controller as well. OK. This is just to give you an idea. We're not going to cover this in detail, and you don't need to understand all of this clearly. But this is a more complicated controller than we're going to talk about today. OK, so let's go back to DRAM. DRAM actually has different types also. Even DRAM controllers are not the same fully. Fundamental principles are the same, but they're different because there are different types with different interface optimized for different purposes, like this HDMI interface versus VGA interface, right? There are different interfaces. Why are they there? They're there for different purposes, actually, and for different technologies. Similarly, DRAM has different technologies also. Commodity technology is DDR. There's low-power versions of it. There's high-bandwidth versions of it that's used for graphics, that has been used for graphics for a long time so that you can supply the high-bandwidth demands of graphics processors. That's why it's called GDDR, graphics DDR. There are low-latency versions of it, embedded DRAM, reduced latency DRAM, and some things we're going to talk about later on. There are 3D stack versions where you have a logic layer underneath the memory layers connected somehow. And we'll talk about that. So, and this is actually increasing. The differences between these different types of memories is increasing because we have actually very different processing needs today. But the underlying microarchitecture is fundamentally the same. So fundamentally, if you look at a DRAM array, it's the same. What you've discussed so far is not going to change. A flexible memory controller needs to support all of these different DRAM types, though. And this complicates the memory controller. So we're going to start thinking about why memory controllers are hard to design. So one of the reasons is you need to support multiple of these. You don't always have to, but if you don't, then your flexibility reduces. So you have a clear trade-off between flexibility and the support you have for different types of memories, right? OK, for example, this one has only LPDDR, and I cannot change and plug in something else to this, right? This also has LPDDR, and I cannot change, plug in something else, right? And LPDDR is slow compared to some other memories. OK, and it's difficult to support all types and upgrades. So this is one example from the paper that I referenced earlier, and this is from 2015, right? As you can see, these are some of the different DRAM types. Again, you don't need to know all of those, but this is proliferating. It's increasing. So what are some of the functions of the DRAM controller as opposed to supporting different DRAM, in addition to potentially supporting different DRAM types? So most important one, ensure correct operation, clearly. This means that you need to ensure that DRAM retains data correctly. That's refresh. And whenever you access it correctly, right? Which means that you need to obey the timing constraints. We'll talk more about timing later on. And you need to service DRAM requests while obeying those constraints. And constraints could be not only timing, but they could be resource conflicts. So for example, if there's an access to the bank, you need to keep track of it, and you need to ensure you don't schedule another access. You could consider that timing also, actually. But also a bus, you need to keep track of the data bus when data is going to be returned so that you don't schedule another access that's going to conflict with that return of the data. Channel conflicts. And there are a bunch of other delays. For example, there's a minimum write-to-read delay that you need to obey. You cannot send a read after you send a write to an entire rank because the bus actually needs to be turned around. That's interesting, right? So there are a bunch of these, and I'll give you more of these. Actually, there are, I think, more than 100 of these in modern DRAM. And you need to translate request to DRAM command sequences, because request says, I want the 64 bytes, right? That's coming from the cache, last level of cache. You need to somehow translate it to all of the commands that you need to generate to make sure that access works. On top of that, you need to do buffering and scheduling for high performance, quality of service. So you need to do some reordering, as we've discussed. You need to exploit the row buffer. You need to exploit parallelism in the rank, and the bus management, right? So there's performance issues, in addition to correctness issues. And on top of that, modern controllers try to manage power consumption and thermals. You can turn on or off DRAM chips, ranks, depending on the granularity that DRAM provides, and manage different power modes. Make sense? OK. So where to place the controller? It's actually an old discussion. But this actually is important, even as an architect, because you have trade-offs again. Do you place it on the processor chip where your processors are, or do you place it outside in a separate chip, for example? That's used to be called the chipset. It's still called the chipset, I guess, in the board. There are advantages and disadvantages. Today, most memory controllers are actually on the CPU chip. But let's take a look at the other one. In the past, they actually had their own chips. There used to be a memory controller chip that did memory control. And then they got integrated with some other things. And they had other, they used to do I/O, for example. And then they got integrated into the CPU chip because the CPU chip actually, because of Moore's law, you could put more transistors. But even this, there's a trade-off. So if you actually have a separate chip for your memory controller, now you have more flexibility, right? You can plug in different types of DRAM into the system by changing that chip, as opposed to tying yourself to the processor. And also perhaps less power density in the CPU chip, right? CPU doesn't need to do another memory control as well. If you put it on the CPU chip, you have reduced latency for main memory access. You don't need to go to another chip to access memory, right? That's clear. And that's the main reason why it was actually put on the CPU chip, in addition to the fact that you could do it, right? And you also have higher bandwidth between the cores and the controller, so you can actually communicate more information. For example, the request's importance to the processing core. Whereas if the memory controller is in a separate chip, that information requires some pin, perhaps, right? Unless you can encode that with some other pin, which is usually not the case. So that's one of the major advantages on the CPU chip. For example, if you have a prefetch request, you may want to treat it differently from a real request that a demand request. And if you want to communicate the request type, that requires some pins if the memory controller is in a different chip. There's a question over there. Yeah. See if you can catch it. Yeah.
Why can we reduce the latency if we put it on chip, CPU chip?
Well, because basically you don't need to go through another chip, right? All of your interconnect is on chip. You don't need to go through an off-chip interconnect, which is slow by nature, and you don't need to go through all of that conversion to go off-chip. Right?
But the command will eventually send to the DRAM chips, anyway, right? Or
That's true, but now you have an additional chip that you need to go through. So think about this. You have a single chip, and you have the memory controller inside the chip. Cores and memory controller can communicate with the wires that are on chip that is fast, and then you send it to the DRAM chip. If you actually have memory controller in some other chip, you have the CPU. Now that needs to go through some interconnect to communicate to that chip, and then that chip needs to communicate with DRAM. Okay. Make sense? Yeah.
Okay, so the memory controller is not in the same chip of DRAM.
No,
the first option. No.
That's right. No, that's still not the case. Yes, that would be one of the other cases. Yeah, a better case perhaps. But memory control has so much functionality that it's not compatible with the DRAM process, capacitor-based process.
Okay.
Okay. So this is one example of a modern memory controller. It may not be the best example, but this is one example. So you have a bunch of requests, and you may have an arbiter, and that may feed into these different banks. And you may actually have some bank management logic that is over here. So you basically need some scheduling at the higher level. So because you're receiving some requests, you may do some scheduling over here, and then you translate the address, figure out which bank the different requests go to. And after that, you can actually do scheduling at the command level also, because now you generate commands. And there's also electrical signaling, which we're not going to talk about in this course. That's also part of the design of the controller, but that's more the I/O interface. This is another view, an even higher level view from a paper that you may read in the future. But there are design choices over here also. For example, this is showing that you get requests from different L2 caches from on chip. There could be a crossbar. Basically, they can go to different bank buffers. And each bank may have its own request buffer. Each bank may have its own scheduler, and which selects a request to schedule. And then you might actually have another level of scheduler over here that selects which bank's selected request to prioritize over here. So this is one design. If you look at this design partitions the request buffer across the different banks. You could have a monolithic design where you have a single request buffer, and a scheduler looks at that single request buffer. And you have the same issues with static partitioning versus dynamic partitioning of a request buffer. Right? So in this case, for example, if all of your requests go to bank 0 and bank 0 doesn't have enough request buffers, you cannot use those request buffers that are dedicated to other banks. Right? Whereas if you had a monolithic request buffer that is shared across banks, you could actually dynamically share that. So it really depends on your load on the banks. And a lot of actually modern schedulers do this design, but other designs are possible as well. OK. So we could go into this also, but I'm not going to go into this as much. You just need to know the fundamentals. OK, scheduling policies. We've discussed this briefly before. I'll talk about the simple ones today, but we'll talk more about scheduling policies when we talk about resource management, because this really deals with resource management. Memory bandwidth is a resource, and you need to manage it across different requests. Very quickly, the first one is not really a scheduling policy, if you will. It is one scheduling policy, but it's first come, first serve, right? You receive the first request, and then service it first. So it is a scheduling policy, but it's really the most basic you can come up with. What else can you do, right, if you don't have that policy? So this is really oldest request first. The second one over here is first ready, first come, first serve, which we've seen. First, basically, it prioritized row hit requests over other requests. And all else being equal, it prioritized older requests over other requests. And the goal, as we've seen, is to maximize row buffer hit rate, because that's useful, because that reduces DRAM latency and also maximizes DRAM throughput. Latency and throughput are related in this case, because you serve one access with much, much reduced latency. You can actually serve more accesses by doing so. So in this case, you can reduce both latency and DRAM throughput. But you may actually be delaying some other requests, right? You may actually be affecting other request latency. So your average latency may go down, but some important requests may be delayed, as we've seen in the past. So I'm going to take a break in 5 minutes or so. So actually, scheduling is done at the command level, as we've discussed. You don't schedule at the request level. You could potentially reorder at the request level, as this shows. But then eventually, you need to do the scheduling of the commands. You need to say, I want to schedule the column commands first over row commands. That's what first ready, first serve means. Because column commands are to open rows, and row commands are opening new rows. So column commands are read and write to an open row. Row commands are activate and precharge. And within each group, older commands are prioritized over younger ones. So this is the command level version of this FR-FCFS that we discussed. And we've talked about the DRAM bank operation, so I'm going to skip this very quickly. You should know this. I just put this over here to remind you. OK. So a scheduling policy is really a prioritization order in the end, request or command prioritization order. There could be many, many considerations over here, right? It could be based on request age, that's oldest first. But you could also incorporate request age in something, in other things. Row buffer hit miss status, request type, prefetch, read, write, evicted. Well, write in this case may be evicted request, right? Because if the requests are coming from write-backs from your last level cache, the only write requests you're seeing would be those write-backs, evictions. But then in modern processors, you actually have uncacheable accesses also. You could actually directly write to memory, bypassing the caches. So you may actually see true write requests, not evictions. So requester type is the load miss or store miss. This is important, right? Maybe load misses are more important, whereas a store miss, you're just going to write the data over there in the cache. And if you already have a sub-block cache and you want the remaining parts of the blocks, this is not on your critical path, right? And you could actually do a lot of write buffering in modern processors so that stores are not on the critical path. Request criticality, if you can somehow say this request is more critical than the other one, right? Maybe to the user, maybe to the processor. If the request is going to stall the processor versus some other request is not going to stall the processor because it's going to be overlapped by some other request, that's also important. Is it the oldest miss in the core? That could be one heuristic, potentially. How many instructions in the core are dependent on this request? How much computation you're going to unleash if you actually service this quickly? Will it stall the processor, as I just discussed? Interference cost to other cores. Is this request going to delay some other cores a lot or not? ... So there's a huge design space over here, some of which we're going to cover when we talk about resource management. But this is to get you thinking. We just talked about two simple policies before, right? OK. Any questions? I see you have the catch box. Did you have a question or not? OK, you just want to keep the catch box.
Well, not necessarily, but.
OK. OK, let's talk about row buffer management policies, and I'm going to stop. So we've talked about stop for a while, not for the entire day. Not yet. We've talked about the different rows, right? Open row means, so this is a design choice, right? You don't need to keep the row open. But it makes sense to keep the row open if the next access is going to come to the same row, right? Or if you're going to have some accesses that are going to come to the same row, and you can schedule them while the row is open. So that's a policy. Open row policy is one row buffer management policy that says after I activate a row, I'm going to keep it open and wait for another access going to the same row. So this is good. If the next access needs the same row, then you'll get a row hit. But if the next access needs a different row, then you'll get a row conflict. And if you have no other access to schedule, right, to the same row. So you get a row conflict and you get wasted energy. As opposed to if you had closed the row, meaning pre-charged the bank, then you would have made the next access quicker. And why wasted energy over here? Because keeping the row actually open wastes energy. An open row actually gets connected to the cells, and you basically have a feedback loop. It's an activated row buffer. You waste a lot of dynamic energy by keeping the row open. So there's a trade-off. The other end, the other opposite end is closed row. Whenever you access a row, activate a row, after you're done with the read, or after you're done with all of the reads that you can see in the memory request scheduling buffer, close the row automatically. Basically, if no requests are already in the request buffer that need the same row. Now, the good thing about this is if the next access needs a different row, you avoid a row conflict. That next access is faster because it doesn't need to do the pre-charge itself. You've already done the pre-charge. You already closed the row. But if the next access needs the same row, you're unlucky. Then you need to have an extra activate latency. If you had kept it open, then you would have avoided that extra activate latency. Make sense? So even this simple design decision affects your performance and energy, as you can see. Or you could have more intelligent policies that are adaptive, right? You could predict whether or not you're going to have an access to the same row in the bank in the near future. Now, if you can do that intelligently, you could get the best of both worlds. If your prediction is, yes, I'm going to have an access to the same row in the same bank, then you keep it open. Otherwise, you close it. So this has implications on performance and energy, and modern controllers actually use a lot of adaptive policies that we're not going to go into. But this is just to give you an idea of how the policy affects what commands are needed for different accesses to a given bank. So if your policy is open row, if your first access is to row 0 and the next access to row 0, you get a row hit, and the next access requires only a read. I'm not going to go through this. This is just for your reference. It's obvious over here. So basically, you want to, let's see. Yeah, you want to avoid this case, for example, right? If your policy is closed row, if the first access is to row 0, and if the next access is to row 0 also, you have a problem because you close the row after the first access, which means that you need to activate the row again. And while you're activating the row, you're basically wasting a lot of time because that activation takes a lot of time. While you're activating the row, you can actually, that's the access you're having. Pre-charging the array also gives you wasted time. So a stupid policy would be actually closing the row after every access, right? Without even looking at the request buffer. Because if your row is open, at least you can design your memory control to look at the request buffer to see if there are other requests to the same row. If there are other requests, then you don't close it immediately. OK. OK, let me see what I have over here, because I think I can cover this, and then we can go into something else. OK, let's talk about power management, because this is related to row buffer also, because if the row buffers are active, they're actually consuming power. But in addition to that, DRAM chips have some other power modes. Unfortunately, maybe not enough power modes today. Basically, the idea is when you're not accessing a chip, power it down. Closing the row buffer is one example of powering it down, reducing at least part of the energy that you spend. And modern memory controllers actually close the row buffer. If they don't see accesses for a while, they basically close the row buffer. But on top of this, there are a bunch of other power states. Active is the highest power. Actually, accessing is the highest power. But active is the second highest power, which you're not accessing, but the bank is active, meaning the row buffer is active and it's connected. There's something in the row buffer. All banks idle is another power state. Power down, you can actually power down the banks. You're not accessing it. And there's also self-refresh. Basically, you actually get rid of all of the power except for the refresh circuitry. Remember that little refresh circuitry in the DRAM chip picture that I showed you? That's the only thing that's active in this case. Now there are trade-offs, of course. Basically, state transitions, transitioning between these different states, you incur latency because you're powering down components or powering up components, and that takes time. And during these state transitions, you cannot access either the entire chip or parts of a chip. For example, if you want to go into the self-refresh mode, it takes some time. But you have the lowest power. In that case, you're only doing refreshing. But if you want to get out of the self-refresh mode, that takes even longer. And you don't want to go into the self-refresh mode only to be woken up by a request that you need to service. Right? So right now, for example, this phone is in self-refresh mode, I bet. I hope, at least. But that self-refresh is consuming my battery, right? Right now, it woke up because I touched it. Maybe it got out of the self-refresh mode. I'm not sure, but that makes sense to me. OK, this is a really good place to stop, I think. Let's take a break for 7 minutes. I think so. OK, for questions on the homework, you can come to the office hours. And TAs will be prepared to give you some help. And the office hours are posted online. They're what? Oh, Moodle forum is also. But somebody was saying his question was not answered on Moodle. So office hours is a good place also, as well.
No. Yeah, I want to say something regarding that question.
So, we will answer questions in Moodle if they are concrete enough. Please sometimes.
Yeah. OK.
So it's like more concrete question, and also feel free, all of you, to take part in the discussion.
So to clarify the policy, for homeworks, you can actually, I'm more than happy if you guys work together, but you should submit your own individual work in the end. For labs, they should be individual. If it's going to be group work, we will declare that. So for homeworks, feel free to work together. But please come to the office hours also. The TAs will be prepared to go into detail. They won't solve the questions for you, but they can give you hints.
One question, can we just discuss about Moodle? Like, if somebody's posting answers on Moodle, can we just make it not being a spoiler? If, like, somebody says, oh, the solution for this is super obvious, it's 64 bytes, and then I get an email and I see, oh, 64 bytes, great. Can we just, like, make some agreement that they're going to put it in white, so we need to select it if we want to read the content? Like, the color of the text is going to be white, so it's not going to appear instantly for us. So we need to.
So there shouldn't be any solutions posted to Moodle.
No, but like somebody, like the last question was basically somebody posted, I don't know, he just said like, oh yeah, the solution for this is 64 bytes. It's obvious. What is the next?
Oh, I see. OK. So you had the solution. I see. Yeah, try not to put the solutions to to Moodle. Just try to ask clarifying questions. And if you need more help, come to the office hours, or talk with each other to discuss. So because it's fine if you actually brainstorm with each other to try to figure out how to solve a problem. I think that's homeworks are a good way of doing that. OK? So I think it's a good idea not to put any solutions. OK. Actually, you can find the solutions somewhere on the web, I'm sure. But that's not the goal, right? The goal is to figure it out on your own. That's how you learn. OK. Let's continue with DRAM control. Basically, I've given you examples of what you can control, but DRAM control is actually more difficult than it looks like. And why? Hopefully, I've given you some reasons, but some more reasons. You need to obey the DRAM timing constraints, and we've covered some, right? For example, you need to activate a bank before you can access a row, and there's some implicit timing constraint. That activation takes some time, and you cannot access DRAM before that activation. You need to figure out whether it's a row hit or a row miss, and that read access, the column command that you send, it takes some time, and you cannot access data before that time. And you need to pre-charge a bank before you can actually do something else to it, so that's a timing constraint, right? You need to prepare the bank for the access. Those are all example timing constraints. And there are many timing constraints in DRAM, more than 50, actually more than 100 in some cases. There's another example over here, write-to-read latency, minimum number of cycles to wait before issuing a read command after a write command is issued to the entire rank. TRC, this is the minimum number of cycles between the issuing of 2 consecutive activate commands to the same bank. This is actually the latency parameter that's used to evaluate the latency of most DRAMs, basically. If you have bank conflicts, you're really bound by this TRC latency, right? 2 different activate commands to the bank. That's the fastest you can activate different rows in DRAM. And there are many others, some of which we are going to see. On top of that, you need to keep track of many resources to prevent the conflicts. Not only to prevent the conflicts, but also keep track of the timing constraints, right? All of these things over here. Channels, banks, ranks, data bus, address bus, row buffers. You need to handle DRAM refresh. You need to manage power consumption. You need to optimize performance, right? All of these affect your performance somehow, how well you handle those timing constraints. For example, write-to-read delays. If you have a write-to-read delay, you cannot do a read before you finish a write. It makes sense to batch the writes and then batch the reads, right? And actually, modern controllers do that. You cannot do a read access to a bank if you're doing a write access to it at the same time, because the bus needs to be turned around. The bus, at any given point in time, it's in one direction. And there's an overhead, TWTR, where you cannot access the rank at all after you've done the write access. You cannot read the rank at all after you've done the write access. So modern controllers, what they do is they have these modes, write mode and read mode, and they accumulate some write requests to different banks, or to the same bank, whatever comes. And when the write buffer, that buffer where you buffer the data that's going to be written to DRAM, is almost full, or above a high watermark, high threshold, they basically switch to this write mode from the read mode. And then they do writes. They flush out the writes into the DRAM in some order again. That ordering may matter. And once they're done, they go back to the read mode. So they operate that way, basically, in a batch mode, because of the way the technology operates. Right? You cannot do a write and a read at the same time. And batch mode makes sense because you want to minimize, amortize these dead cycles on the bus, right? Because this TWTR means that you cannot do an access, you cannot do a read access to the bus after you do a write access. Okay, so that affects your performance clearly, and that affects your quality of service. So you need to optimize it as a memory controller. And that reordering is not simple. There's also effect on, if you want to do perfect reordering, for example, even if you figured out the perfect algorithm to optimize a request, even reordering, implementing reordering is not simple. That has effects on energy, complexity of the design. And also there's fairness and quality of service, which we will talk about, that complicates the scheduling problem. Because your goal is not just performance, perhaps, but to be fair to different applications. Or some applications have performance guarantees that you need to satisfy, right? For example, if you're actually displaying something on the screen over here, the GPU that's generating that perhaps needs to be prioritized at that point in time. And CPU may need to be delayed, even though that may also be doing something important, right? And they both go through the same memory controller. So there's a problem. And there may be other accelerators that are going through the same memory controller. For example, a video accelerator that's accessing the same memory, right? OK, so this actually complicates the design a lot. And we're going to cover that more. But let's take a look at some of these other ones first. So there are many DRAM timing constraints. This is just an example over here. And you can read the papers that we have referenced. So this paper, for example, deals with how to reduce the write overheads, write-to-read switching overheads in DRAM. That's one example. And this lists some of the timing constraints. The paper that I recommended to you lists some other timing constraints. I'll go over this relatively quickly, give you some examples. This is from a paper that I recommended over here. But basically, this is, so if you look at the DRAM sheets, this is very difficult to understand. That's why I'm recommending you some of these papers. And if you look at some other sources, this is also very difficult to understand. This is one relatively easy way to understand. For example, this is a bank. It's in a pre-charge state, meaning it's ready to access. Pre-charge means you set the bit lines to a level where you can detect the perturbation on the bit lines, right? Now, if you activate it, if you activate this word line, activate this row, you basically, what happens is basically charge sharing. The cells on that word line share their charge with the corresponding bit lines, and they perturb the bit line, basically. Now, that starts the activation process. The activate command stands the activation process. After some point, what happens is there's the sense amplifiers kick in, and they start amplifying the data. But they've sensed the data. They figured out that this actually is storing a 1. This has charge in it. But this other one doesn't have charge in it. This is storing a 0. At that point, you could actually issue a read command, right? And that's where the activate to read latency comes in. it basically determines when can you issue the read command after you've activated the bank. And that's there for a reason, because the sense amplifiers become ready to be read at that point. And in this particular DRAM, it's about 15 nanoseconds. So if you look at this paper, this explains these constraints. That's called the TRCD over here. It's basically, the name of the command is TRCD. It's an activate to read to write. The scope is bank. It's applied in a bank. And it takes about 13 to 15 nanoseconds. Right? So after you activate it, the sense amplifier is still operating over here, basically. The sense amplifier is, remember, the next step of the sense amplification is restoration of the charge. So the sense amplifier figured out that this is a 1 and this is a 0, but now needs to restore the data back into the word line that you're reading, or the bits that it's connected to. So that takes some time. Even though you can read the sense amplifier, you still need to restore the data back into the cells, and that takes some time. And that time, until that happens, until you actually have restored the data that you've destroyed by reading, that's the nature of DRAM, until that happens, you cannot do another access, some other access. That's why you have a time constraint between activate and a precharge. You cannot precharge the bank until you've ensured that you restored the data to the row that you've destroyed. Hence, that's the reason for that timing constraint, activate to precharge. And if you can find it over here, it's called TRAS, unfortunate naming, row address strobe, but that's historical. Basically, it's an activate to precharge timing constraint. Its scope is within a bank, and it's about 35 nanoseconds over in this particular technology. Right? And then after that, now you can do a precharge. You're free to do a precharge if that amount of time passes. And once you do the precharge, you need to wait until you get to the stage where you can issue the activate. What does precharge do? Basically, if you look at this state over here, you've amplified the data, you restored the cell. Your bit line is VDD over here because that's actually a charge cell, and your bit line over here is 0 because that's a discharge cell. Because of charge sharing, that's what you get. To be able to access another row, you need to prepare the array for the next access. That's what precharge means, meaning set the bit lines to VDD over 2, such that you can sense the next row that you're going to access, and also disconnect the word line. Right? That's the idea. And that takes some time, and that time is called TRP. You go over here, find it. That's precharge to activate, and it's at the bank level again, and it takes about 13 to 15 nanoseconds in this technology. So these are there all for a reason, because the physical phenomenon takes some time, and we're trying to make the best out of the latency. So we could have said, let me go over a couple of more of these. It's not displayed over here, but for example, TRC is really the combination of TRAS and TRP. Basically, TRC is you have an activate. When can you do the next activate to the same bank without losing data? So it's really TRAS plus TRP. It's 15 nanoseconds over here, as you can see. There's also a bunch of other things. TWTR, for example, write-to-read latency, read-to-write latency. These are, as you can see, these are at the rank level. You have to enforce it at the rank level, not at the bank level. And there's also channel level constraints called CCD. When can you do read-to-read, write-to-write constraints? And these are all there for physical reasons because of the way the circuitry operates. Make sense? Now, you could ask the question, why do we have all these different latencies? They complicate the life. They do complicate the memory controller quite a bit, because now it needs to keep track of all these things. There are alternatives, right? The alternative is have the worst-case latency for all of these different things, and you don't need to worry about it, right? Whatever command you send, you wait for the worst case. And worst case in this case could be 35 nanoseconds, since this is a combination of multiple latencies over here. After every command, you wait 35 nanoseconds. But clearly, that's a bad idea, because you don't need to wait for that long for every command. If you're doing a pre-charge after an activate, yes, you need to wait for 35 nanoseconds, because that's how it takes. But if you're doing a read after an activate, waiting 35 nanoseconds is really unnecessary. Right? So we're complicating things so that we can reduce the latency and take advantage of the fact that different phenomena, physical phenomena, take different amounts of time. Well, you could also say, and people have said this, I don't want to do it this way. This is very synchronous. And as a result of this, I need to keep track of every single thing. Why don't I make DRAM asynchronous, right? Whenever I send a command, and whenever the DRAM is ready, and it figures out, it knows when it's ready, it sends an acknowledgement to me saying, I'm done with this command, right? That's an asynchronous mode of operation. That could actually achieve the benefits of this, potentially. But the problem is now you have a different protocol, right? Your protocol is different, and you need to have a handshake. As opposed to relying on agreed-upon latencies, that asynchronous protocol leads to some other overheads to ensure that you actually get it correct. So there's another problem. That's why we have the synchronous DRAM tape. But that asynchronous, if you design it well, if you can design it well without a lot of bugs, that could be better, actually. The problem is the handshake overhead that you need to have between the controller and DRAM at that point. Yes?
So is there some kind of a handshake every time we plug a new DRAM module in our PC? Like, does the CPU negotiate what are these timings? Or is it just standardized throughout the...
No. So it really depends on the DRAM. So remember the SPD, serial presence detect, that I showed you earlier? Whenever you plug in your new DRAM module, that serial presence detect is red, and you change the settings.
Okay.
Yeah. But that's a one-time handshake, hopefully. Yeah. OK, so there are different design choices, clearly, as I've just shown you. The reason we have this is simple. It's synchronous. You don't need to design that asynchronous circuitry and the handshake related to it. And you can also get, hopefully, the best of latency. But we'll talk about latency even more later. And this is true for many, many other controllers also. If you look at a flash controller, you have these similar timing constraints in a flash controller as well, and even weirder ones that we're not going to talk about at the moment, at least. OK, so this is another. So this is from the sub-array level parallelism paper. You can take a look at it. And this is from another view from the tiered latency DRAM paper, which hopefully we will talk about. This gives you a lower level view of what happens to each cell. So when you activate it, for example, you start the charge sharing. After some point, you have enough charge in the sense amplifier that you can read it. That's the activate to read latency, TRCD. And after some point, you restore the charge into the cell that you actually read. And you can actually start pre-charging. That's the activate to pre-charge latency. And when you start pre-charging, after some point, you need to get the VDD, the bit line to VDD over 2, and that takes some time. That's the pre-charge latency. OK, so it's actually simple. Once you understand the physical phenomenon, there are reasons underneath, and these papers give you the underlying reasons, whereas you won't get these reasons in DRAM data sheets at all. OK, it's actually a good idea to read these data sheets. They're like instruction set architecture manuals. They won't give you the reasoning in most cases as to why they make a design decision. That's why I assign you the papers. And you won't get this reasoning in any book either, unfortunately. OK, so this is actually becoming more difficult. I've shown you this picture before, if you remember. Because the controllers are, not only controllers are getting more complicated, they're controlling more things, right? First of all, they're receiving requests from different heterogeneous agents. They need to hopefully adapt to them, which means that there's more interference between those agents. And there are many timing constraints for different memory types that they may be controlling. And you may have a single controller controlling multiple memory types, or have multiple controllers that are coordinating with each other, controlling multiple memory types. And they need to have satisfy many goals at the same time: performance, fairness, quality of service, energy efficiency, and correctness. Correctness is implied over here, right? So that's one of the reasons they're getting more and more complex. So I'll give you some ideas to stretch your imagination going forward. But basically, reality is it's difficult to optimize all these different constraints while maximizing some metrics: performance, QoS, energy efficiency. Wouldn't it be nice if we had a DRAM controller that automatically found a good scheduling policy of its own, right? So we had this dream a long time ago, about 10 years ago, actually. And as an architect, you always follow your dreams, and you try to make it possible, right? So the idea is in this paper. You don't need to read it. We'll put it online. If you want, you can review it. So actually, we're going to put a lot of papers online. If you want to get extra credit in this course, you can review any paper you like. Do a good job, of course. Don't just copy and paste the abstract and come up with some weaknesses and strengths from the paper. You can easily find the strengths from the paper, but weaknesses you have to figure out on your own usually. But it's good to have, you should have your own strengths and weaknesses. So we're going to put a lot of papers online. But this was our dream, basically, have a memory controller that can do stuff on its own. So the motivation was DRAM controllers are difficult to design. And it's difficult for human designers to design a policy that can adapt itself very well to different workloads and to different system conditions. As I said, things are getting more complex. And we didn't even look at a very complex system over here. So the idea is to design a memory controller that adapts its scheduling policy decisions. In this case, we just looked at the scheduling policy decisions, not even power management or on all of that other stuff, to the workload behavior and system conditions using machine learning. So I think this is one general direction to follow in systems that are really complex going forward. So the observation that we had was that reinforcement learning, a particular form of machine learning, actually maps nicely to memory control. And I'm not going to go into the detail over here, because this requires reinforcement learning theory. You need to have a Markov decision process for this to work well. And it turns out the memory controller can be formulated as a Markov decision process, Markov decision diagram. Anyway, you should read the paper if you're interested in that. So the design is that memory controller is treated as a reinforcement learning agent that can dynamically and continuously learn and employ the best scheduling policy. Okay, so basically, what is reinforcement learning? And in a nutshell, this is a very classic form. You have an agent. It interacts with the environment by taking actions. And for each action, it gets a reward. And it also can observe the state of the environment. And with each action, it can change the state of the environment. Right? A memory control is essentially this, actually. If you look at a memory scheduler, in this case, in particular, the scheduling logic, it schedules a command. And the system changes. You get a data bus utilization immediately, actually, based on the command you schedule. And you can also observe the state attributes and change the state of the system by scheduling the command. Right? So you can view the DRAM scheduler as a reinforcement learning agent. And the goal of this agent is to learn to choose actions, meaning commands, to schedule, to maximize some long-term reward function. Again, reinforcement learning, for this to work, you need to specify a reward function. And how you specify the reward function makes a huge difference. Do you optimize short-term rewards, long-term rewards? In this case, we opted to optimize the long-term rewards. The idea was to optimize for the long-term data bus utilization, maximize the long-term data bus utilization. You could, of course, have different rewards for different goals, right? Clearly, data bus utilization may not be the best choice if your goal is quality of service, because you may actually prioritize an application that's actually really good at utilizing the data bus. But if your goal is performance, well, if your goal is data bus utilization, and data bus utilization is correlated with your performance, then this may not be a bad goal. Okay, so that's the idea, basically. You dynamically adapt the memory scheduling policy via interaction with the system at runtime. The memory controller associates system states and actions with long-term reward values. Each action at a given state leads to a learned reward. And you schedule the command with the highest estimated long-term reward value in each state. Right? You observe the state, and you look at all possible actions. Now you have state action pairs. Each state action pair has an associated long-term reward that you expect to gain if you actually choose that action given the state. And, of course, this is stored in a table in this case. There are many different ways of designing that table. But that's the idea. So you basically pick the action in a given state that is expected to maximize the long-term reward value. And you continuously update the reward values for the different state action pairs based on feedback from the system. And the feedback is really the data bus utilization that you get in this case. Right? And if you want more, you can look at the paper. Actually, I'm going to give you a little bit more. So this is one way of looking at it. You observe the state of the transaction queue, the different transactions, the buffers, and the scheduler chooses an action, and then it gets a reward from the data bus utilization. Right? That's a pictorial way. Of course, you could observe the state of the entire system, not just the transaction queue, right? So let's take a look at what are the different things, at least in this specification. You could build on it and do better, of course. So reward function in our case was relatively simple. We basically had a positive reward for scheduling read and write commands. That's data bus utilization. And you got 0 at all other times. Again, the goal is to maximize long-term data bus utilization. So reward function is really considering long-term utilization. That's why we have this term with R's and yeah, you want to maximize this basically. And so some of these actions happened in the past and they're weighted with different weights. Okay. And state attributes, which state attributes to look at, that's a problem in itself, right? What do you look at to decide your state action pairs? And these were the things that we had selected. And for this, actually, you use another statistical technique, which is feature selection. So you actually need to somehow select the features that you look at. And then there's a design option, of course. Do you do it statically or do you do it dynamically? Do you select the features at which time? In our case, we did it statically. Basically, at the design time of the memory controller, these features that it's going to look at was fixed. So for that, you need to do a lot of simulation, of course, to figure out which features are important. But that you need to do as a designer. So that's the difficult part of designing this controller, specifying all of this. So as you can see, number of reads, writes, load misses in the transaction queue. So clearly, load misses, we found that it matters to consider the fact that this cache miss that you're trying to schedule is coming from a load versus a store. And number of pending writes, how many writes do you have? So that actually has an effect. Again, we don't know exactly how this works internally because this is really a black box machine learning. But you could guess that this is an effect on performance because writes and reads have this tension, right, as I discussed earlier. You cannot do a write while you're doing a read, and you cannot do a read while you're doing a write. And that's why the designer is still important in figuring out what these possible state attributes to look at might be to feed the feature selection algorithm. And reorder buffer heads. These are basically instructions that are at the top of the reorder buffer, meaning that are really blocking the processor from making progress, waiting for the reference row. So you can see that this feature is actually very specific, but it's important because you consider the reference row and you look at how many processors are actually waiting for that reference row at that point in time. And actually, not only how many processors are being stalled for that reference row. And the request's relative order in the instruction window of the processor. Is it at the top or is it at the bottom? Is it just fetched? So that determines how much overlap it has with other instructions and other memory requests. So clearly, we came up with it. So as a designer, you really need to know what kind of features you feed, because the algorithm in the end is only as good as what features you feed to it. If you didn't come up with good features, perhaps this would have been a disaster, right? And actions, these are some actions. So activate clearly things that we've discussed so far, but we actually distinguished between a load misread and store misread, and a preemptive precharge. Remember, you can actually have a preemptive precharge as opposed to a precharge to a particular pending row that has a request to it. And a no-op. Actually, no-op could be an action too. Sometimes you may decide not to do anything, right? That's not necessarily a bad thing, because you may actually get a request, for example. If you wait for a while, you may get a request that will hit in the row buffer, right? As opposed to, and then you wait for it, and then you actually service it, and then you close the row after that. Most modern memory controllers don't do no-ops. They try to do something. But we find out, actually, this no-op is actually important. OK, so these are important in, I think, whenever you're designing anything that works with machine learning. So let me give you the performance. If you want more detail, there's more detail in the paper. But it doesn't go into the detail as to how you do the feature selection, of course. That's the art part of this. Even if your memory controller is a black box, what you select for that black box to observe actually makes a huge difference. But let me give you some performance results. These are actually parallel applications. These are 4-core. I think it's on a 4-core system. But you can read the paper. So these are different scheduling policies. This is geometric mean. OK. I don't want to talk about the applications, but these are actually really interesting applications. For example, eQuake is an earthquake simulator. And there's a bunch of other things over here as well. If you look at the first ready, first come, first served scheduler, that's the performance result is optimized over that, basically. That's one means that. In-order scheduling does a really terrible job over here, as you can see. The performance is 58% of this first ready, first come, first served scheduler. So FCFS is not a good idea. Optimistic means if you're magically able to get rid of all of the timing constraints, except for the data bus. So here, the data bus is the constraint, but all of the other timing constraints are gone, which is good, right? Then you would get 70% performance improvement compared to first ready, first come, first serve. So that gives you the headroom, but it's not achievable probably because how are you going to get rid of the timing constraints, right? And the RL-based, reinforcement learning-based scheduler actually provides you about 19% performance improvement compared to first ready, first come, first serve. which is not bad. I think it's not easy to obtain that sort of performance improvement. And this is some sensitivity study that you can look at in the paper if you have interest. So the performance improves if you actually have multiple channels. OK, so that's the idea, basically. Of course, how you design it, I didn't even talk about it, right? If you want to learn about the implementation, that's in the paper again. But clearly, there are some advantages and disadvantages to it. I'll go through these. Basically, advantages, you can adapt the scheduling policy dynamically to the changing workload behavior and maximize a long-term target rate. Whereas if you look at what we've discussed, first come, first serve clearly doesn't adapt. First ready, first come, first serve has some little adaptation because it considers the row buffer hit rate. If you have a good row buffer hit rate, you exploit that, right? But it's not extensive. Now you can adapt much more extensively. And you reduce the designer's burden in finding a good scheduling policy. But you shift the burden somewhere else, right? Now the designer needs to specify what system variables might be useful, and that's part of the art, and what target to optimize, but not how to optimize it. Right? That's the reward function, basically. And this is the state attributes. And of course, you need to specify the actions, but actions are a little bit less important because it's, you already know what kind of actions you need to do in a memory controller, right? But of course, it has, like any idea that we will talk about, it has disadvantages. One disadvantage, actually, is the fact that it's a black box turns out to be a disadvantage because a designer, a human designer, tends to, at least architects, tend to be much less likely to implement what she cannot easily reason about. Here, you're not able to reason about it. Even though you get better performance, people are actually reluctant to implement something that you cannot easily reason about. So that's one of the reasons why this is not implemented today. And there needs to be more research, I think, going forward to figure out how to do this. And of course, how do you specify different reward functions that can achieve different objectives? That's an open question also. Because your objective is not just data bus utilization, but that reward function is easy to define, right? The other reward functions make life a little bit more complicated. How do you incorporate fairness, quality of service, ... Yes?
So do you compute the policy online or offline? So if you do it online, that's a lot of overhead. If you do it offline, how do you know all those, like, all those pairs, like,
yeah. So the,
policy you need to have a reward to make it.
Sure.
How can you collect all those data?
Yeah, the policy is all done online because you have a lot of data, a lot of requests coming in, so you can actually do it online. The overhead is the hardware implementation overhead. You need to have a table, basically, to actually store those state action pairs and the associated rewards. You can read the paper for more detail. There's a particular implementation. It doesn't come for free, sure. There's additional overhead, so that's part of the disadvantage over here. The last part, hardware complexity. So certainly it comes at a hardware complexity cost. I think the table that we had was about 32 kilobytes on the memory controller, which is large. It's not, but it's not 1 megabyte. That's good to know. But it does come at a complexity. But it does, the complexity, I mean, as an architect, again, remember the $4 billion Oculus? There's no way you're going to gain something without paying for something. So it's always a trade-off. The key question is that 19% important enough for you to bear that complexity, right? Clearly, that $4 billion was good for the Oculus, for the New York people, or at least for whoever made the decision for New York people. Okay. So as an architect, you have to change something to get something, and that's the cost that you pay. That's why in this course, we'll always have advantages and disadvantages. And usually, with ideas that actually change something, there's usually this part, complexity, cost. Out-of-order execution is one of my other favorite examples, right? We could execute instructions in the order that's specified by the program, or we could have this complicated logic that figures out which instructions are independent and tries to schedule them earlier. That clearly comes at a big cost. But all modern microprocessors actually implement it today. All modern high-performance microprocessors implement it today. But that didn't used to be the case 30 years ago. OK. So how do you minimize the complexity is important, of course, right? You don't want to have a huge complexity. You want to minimize it. And the paper discusses that. OK, so that's your reading. But you don't need to, this is not a required reading. Again, extra credit. OK, I think this takes me to some place that I wanted to discuss before you start your labs so that you have a good idea of simulation and evaluation methodologies. So a really good time. We'll take a break again at 15. You guys are doing well? Any questions? Was this interesting? I think this is, there's actually a lot more research opportunity in this area. So if you're interested and if you want to talk with me, I'd be happy to talk, because systems are becoming more complex and we need to do more and more such things in every part of the system, especially in a multi-core system today. And at some point, these will be the future. So maybe you look 30 years from now, you will see a lot of agents that operate based on these principles. Maybe not exactly this principle, but something that's more intelligent than what we have today. OK, so that brings me to evaluating new ideas for new architectures, new memory architectures, but architectures in general. So whenever you have this idea, for example, reinforcement learning memory controller. OK, good, you've designed this. How do you evaluate it, right? Do you go out and build a chip that does it? Well, like, we could have done that, but that would have cost us a lot, probably. I don't know about $4 billion, but it could cost a lot. So basically, the question is, how do we assess an idea will improve a target metric X? X could be anything. And we have a variety of evaluation methods that are available as an architect, right? One is theoretical proof. That's very difficult to do, unfortunately, in the systems we have today. Analytical modeling and estimation. For example, you could have a spreadsheet that takes in some important parameters, and you generate an analytical model that somehow models your idea and figure out what would your metric X improve by, right, based on those spreadsheet analytical model. Of course, you need to verify that analytical model somehow so that you can trust it. But this is actually done as an architect a lot. This is very hard to do, as you can imagine. But this is, it's very hard to prove that an idea will work. And we will discuss why. But a lot of people do this analytical modeling very quickly to decide which very high-level ideas to potentially explore. It doesn't work with every idea, of course. A big tool is simulation. And this comes at varying degrees of abstraction and accuracy. I'm going to talk about this more. So the results that I presented to you on the reinforcement learning-based memory controllers was based on simulation. It was a simulator that was modeling the system and the workloads and the memory controller. And we modified the simulator and compared different memory scheduling policies. Right? That's easier to do, of course, than theoretical proof. That's potentially easier to do and more accurate to do than analytical modeling. But this is not the only way. You could prototype with a real system. You could put this on an FPGA, for example, and try to get some results. It's not clear if this is better than simulation, but there could be cases where it's better than simulation. And the last thing may be a real implementation, right? You just say, oh, I designed this, and I go and implement it. That's usually not desirable in architecture, because at least immediately, because you need to prune the design space at least a little bit, right? And how do you prune the design space? It's usually with some of these techniques, at least the 3 of the techniques in the middle. And simulation has been the most prevalent of it. Because of the difficulties. The difficulty is the answer that you have to this question is usually workload dependent, right? And workloads are not easy to model theoretically or even analytically, today's workloads. For example, even caching, right? Even an idea like caching is very much workload dependent. If you have random access, your cache doesn't work. In fact, your cache is worse if you have random access because you've added some extra latency to serve those random accesses, right? Pipelining, even pipelining, right? Even a simple idea like pipelining is workload dependent, right? How much dependencies you have, what your pipeline looks like. And any idea we talked about, RAIDer, memory scheduling, they're all workload dependent. Of course, it depends on your metric also, right? RAIDer, for example, can reduce refreshes without dependence on the workload, perhaps. And workloads change. And the system has many design choices and parameters. So you're not only looking at this idea. That would be very myopic, right? You're really looking at this idea within the context of the broader system. And you actually need to decide many ideas and many parameters for a design at the same time. And your idea may affect some other part of the system because you're doing a trade-off, for example. The trade-off in reinforcement learning memory controller may be, oh, we're adding this large hardware to the memory controller to optimize memory scheduling. But we could have added that to the cache as opposed to adding it to the memory controller, right? What would be the performance benefit of that, assuming X is performance, right? So now if you actually want to answer that question, well, forget about real implementation, right? How many real implementations can you do to evaluate all those possible answers? So not easily to evaluate all possible combinations, even in simulation, right? Okay, and system parameters may also change, right, as you develop the system. Maybe you want multiple parameters. You don't want a single parameter. So you actually have a huge design space to deal with. And you're also affected by the workloads on top over here. That's the nice thing about architecture. You're really affected by the software on top and hardware at the bottom and all of the design choices that you have. That's not necessarily true for circuits, for example. If you're designing a circuit, you're usually not affected by the software, right? You can actually treat that as a black box, if you will. OK, so let's talk about simulation. I think of this as the field of dreams, right? Because as an architect, you're really, in part, you're a dreamer. You're really creating something that didn't exist before. And the simulation is really a key tool of the architect for the reasons that we've discussed just now. You have other tools, and you need to figure out what tools to use, actually. But simulation is really a key tool because it enables the exploration of many dreams at the same time, concurrently. And simulation is very nice because you can actually explore many, many dreams concurrently. You can farm it out to a data center. Right? We used to have this joke at the different companies that I worked at. People build these data centers so that you can build new processors and new systems, right? Because you could actually have a lot of simulations that are ongoing. And also, it enables a reality check of the dreams, right? You can actually test your dreams and deciding which dream is better, if you want to dream this or that, right? And there are many, many dreams you can potentially have. And it also enables the ability to fool yourself with false dreams, unfortunately. That's the downside of simulation. That's the downside of all of the methodologies over here that we've discussed in the previous slide. But simulation is especially prone to something like this. Because if you don't model something really important, for example, you may think that you improved metric X, but you actually, in reality, you would have reduced metric X, right? So this is also an art, figuring out how to do this. So we will do some high-level simulation in this course, but I'll motivate it. So for the first lab, you're actually doing low-level simulation. Not at the lowest level that you could possibly do, but you're actually doing RTL design and RTL simulation. But the problem is if you keep doing RTL, not even a real implementation, we're not even considering that at the moment, RTL simulation is intractable for design space exploration. It's too time-consuming to design and evaluate a Verilog design for everything. For example, even for the reinforcement learning memory controller, it takes a lot of time to do the RTL simulation for a real workload for a long enough time, right? Especially over a large number of workloads, right? If you want to actually study a huge number of workloads, it really becomes intractable. And especially if you want to predict the performance of a good chunk of a workload on a particular design, right? And the workloads we have today, so in RTL simulation, perhaps you can wait for a day and you could execute 1,000 instructions, right? Something like that. But the real workloads take, I don't know, trillions of instructions, or even more, right? Some of these workloads never end. It depends on the data sets. So how do you actually simulate that? And especially if you want to consider many design choices, cache size associated with block size, different algorithms, memory control and scheduling algorithms, in order versus out of order execution, I can build this list. So it's not even possible to design a system where you could explore all of these design choices in RTL, in Verilog, right? I mean, if you could do it, that's great. Then you could actually win the Turing Award, maybe. And let me know if you do it. The problem is it's very difficult to do, at that level, at least. That's why we resort to higher-level simulation, more abstract simulation, C-level simulation, for example, so that we can explore the design choices quickly to see their impact on the workloads we're designing the platform for. Right? That's why we have analytical models also, although analytical modeling is even more dangerous. Right? You can even fool yourself even more over there if you miss some key parameter, for example. And you may not even be able to model the workload very well with an analytical model. That's the downside of an analytical model. Whereas simulation, you can run the workload on at least a make-believe system that is trying to do what you're actually targeting, trying to do exactly what your target system is going to do. OK, so there are clearly different goals in simulation also. One is exploring the design space quickly and see what you want to potentially implement in a next-generation platform, or propose as the next big idea to advance the state of the art. So in this case, the goal is mainly to see the relative effects of the design decisions. Your goal is not really to get, oh, I improve performance exactly by 10.5%, right? Your goal is to really prune the design space and say, oh, I want to do this. Now you can go into some other level of fidelity of simulation such that you can really more seriously evaluate what is the exact performance improvement, for example. So this is actually an important goal. That's the goal that people have in research, for example, or some ideas that you can potentially implement in a next generation platform. You're working for, let's say, Intel, and you're the chief architect, and you have a bunch of architects that are working with you. You basically want to make a decision. Am I going to have a memory scheduler that has reinforcement learning in it, or am I going to have a memory scheduler that doesn't have reinforcement learning in it? Right? You're not decided yet, but you want to figure out. But there's another goal in simulation, which is very, very different. It's to match the behavior of an existing system so that you can debug and verify it at cycle level accuracy. Right? And propose small tweaks to the design that can make a difference in performance and energy. Right? And that's very different. The goal in this case is very, very high accuracy so that you could actually really mimic the system that's existing, and you could actually figure out what you can do better, slightly better. Not necessarily a huge, big idea that can change the entire system. Right? And there are a bunch of other goals in between also. And actually, there are people at companies that do this, that are really dedicated to this. You already designed Pentium 4, let's say, and so you already have a high-level simulation model that you use, but you want to tweak that high-level simulation model to match the behavior of this exactly, almost exactly. Exactly is very tough in general. So that you can actually understand what's going on, what are the bottlenecks in the design, and you can fix them in the next generation of Pentium 4, for example. Pentium 4 is old, but that's an example. So there are a bunch of other goals in between also. You can refine the explored design space without going into a full detailed cycle-accurate design. Or gain confidence in your design decisions made by higher-level design space exploration. Basically, these are not exactly these goals, but somewhere in between. And you may need to have different simulators for this. So there are clearly trade-offs in simulation. And usually there are 3 metrics when we evaluate a simulator. One is speed, how fast you can run a particular workload. Second is flexibility, how easily you can modify it. And the accuracy, what is the fidelity of it compared to the real system. The real system may not exist. The system that is supposed to be real at some point, you want to be accurate to that system, right? So speed is how fast the simulator runs. It's instructions per second, for example, or cycles per second, or slowdown compared to a real system if you're really actually trying to match the behavior of a real system, right? If your simulator is the same speed, like slows down by 1x compared to the real system, that's great, right? How do you do that? Again, you can win the Turing Award if you do that. Clearly, there's an overhead in simulation. Flexibility, how quickly can you modify the simulator to evaluate different algorithms and design choices? Clearly, this is important if you're doing design space exploration. And that's one of the very, very important things if you want to do research especially. Or actually design a completely different system from scratch, right? Which people do actually once in a while. And accuracy, how accurate the performance or whatever metric numbers the simulator generates versus a real design. That's the simulation error. And again, as I said, real design may not exist. For example, how accurate are our reinforcement learning memory scheduler numbers compared to real design that employs the exact reinforcement learning mechanism? That doesn't exist, right? That's the difficulty here. OK, so the relative importance of these metrics, of course, varies depending on where you are in the design process and what your goal is. So initially, for example, you want very high flexibility and very high speed, but maybe you can trade off accuracy a little bit. Because you don't want to be completely accurate. You want to get the big, high-order bits right. I want to implement this versus that. And how I implement this, I'll figure it out later on. So these are usually trade-offs. And usually you can get at most 2 of these, but not all 3 at the same time. OK, so speed and flexibility clearly affect how quickly you can make design trade-offs. And accuracy affects how good your design trade-offs may end up being in the end. And also how fast you can build your simulator. That's also important. We didn't talk about that speed, right? That's another speed. Because usually it takes time to design these things. And how fast you can build and model your simulator is one of the functions in time to market a system. If you keep on building your simulator, you may never market your system. And actually, I know real projects that suffered from this, where people took too long to build a good enough simulation platform. And as a result, they got delayed and delayed and delayed. So this is also important. I didn't talk about that in the previous one because it's really not a choice of, well, it is actually part of the thing, but it's kind of an interesting aspect. Okay, flexibility also affects how much human effort you need to spend modifying the simulator. That's another issue, actually. If your simulator is too detailed, somebody else may not be able to modify it, or you may not be able to modify it easily. So that affects your design time also. So there are interesting trade-offs here. Okay, I mean, this is clear, hopefully. So high-level simulation, the key idea is to raise the abstraction level of modeling to give up some accuracy to enable speed and flexibility here, and quick simulator design, again. So the key advantage in high-level simulation, like everything else, it has an advantage and disadvantages. You can still make the right trade-offs and can do it quickly, assuming you do the art right. All you need is modeling the key high-level factors. You can omit corner case conditions. That's the thinking here. As an architect, again, that could be good, right? And all you need is to get the relative trends accurately, not exact performance numbers. That's why you can, assuming you can do these right, and this also actually is a lot of experience and art, again, because how do you know whether you're getting these right? Maybe doing it wrong. There's always that potential error. But that's the advantage, to make the right trade-offs and do it quickly without modeling everything. The disadvantage, again, if you don't do it right, you open up the possibility of potentially wrong decisions. And how do you ensure you get the relative trends accurately? That's always an art. Okay. So you can think of simulation as progressive refinement as well. So you start with high-level models. Well, in the end, you start with an idea, maybe some analytical models. But eventually, when you decide to simulate, you build some high-level models, maybe C, abstract level. And then you go into more medium-level models that are more, your fidelity increases as you go down. Low-level models, maybe RTL with everything modeled, and then a real design. And clearly, there are trade-offs, and usually that's how the designs progress. You start with high-level models, and then you make some design decisions, and then you go into medium-level models, and then you make some more design decisions, and you decide to implement something more specific in the low-level model, and then you make some more design decisions, and then you design the real system after that. Because it's too costly to design many, many real designs, right? As you refine, as you go down the above list, your abstraction level reduces, and your accuracy hopefully increases, but not necessarily, again, if you're not careful. Sometimes your high-level models may be more accurate. And we've seen this actually many, many times in computer architecture. Sometimes the power models that you have with very small number of knobs are more accurate than power models that you have where you actually simulate everything in detail. It can turn out that way, right? And your flexibility reduces. Clearly, in a real design, you're not flexible anymore as much. And your speed likely reduces, except for the real design. Real design is really fast in executing the workloads. But the RTL level model is really, really slow in executing the workloads, right? Whereas high-level model is also really fast in executing the workloads. And of course, you can loop back and fix higher-level models. And this is really the simulation flaw in a company like Intel, NVIDIA, whoever designs some platforms. Usually, they start with some analytical models at top and then go down all the way. And then once they have the real design, they can loop back and they can change their models to actually ensure that they're more accurate for the next design they may potentially have. They learn from that flow over time because they go all the way to the real design, right? So that's the benefit of doing all of it so that you can loop back and fix the higher level models. So in a couple of slides, I'll finish. So if you want to make the best of architecture, you actually need to be comfortable at all levels of refinement, unfortunately. You need to do the analytical modeling well, and you need to do all the levels really, really well, including the extremes, I think, because then you understand how to build middle-level models, for example. And you need to use what type of simulation to use when, or what type of evaluation method to use when. And more generally, what type, yeah, that's what I said. And recall that there are a bunch of evaluation methods that are available. I'm not really dismissing this, but it's really difficult to do in systems we design today. People used to try to do it in the past. Actually, if you look at the 1950s, 1960s, they tried to come up with really models of the workload behavior and prove that something works or doesn't work based on those models of the workload behavior. But as workload became much, much more complex, this became very, very quickly very, very difficult to do. So this is usually not an option for what we do in platform design. Although it would be nice, of course, right, if I could prove that this works or this idea improves performance by more than this much, right? Okay, I think this is a good place to take a break. Let's take a break for 7 minutes, and then we'll continue. In different parts.
Yeah.
The issue is in sector cache, they share the tags.
Okay.
Yeah. So they don't have separate tags for each sector.
And then also noise in every sector.
Well, yeah, that's a good that's a question that I will have to, but I'll give you a response. Basically, what you're suggesting is essentially a small block cache.
Yeah. Pretty much.
Which is not sector cache. If you have a sector, you can write to one of the blocks without fetching the other ones. So for example, I want to cache to the vent. Yeah.
That's the
Then
vent.
so you say a vent and
Explain this.
exactly. But you cannot store the two different
Are we gonna do
blocks
it again?
on two different blocks.
You said
I'm gonna do it again, but for me it's better if you're not. That way, because you're always running ahead and doing stuff, and then I always keep stuff. So that's why I did the data plot one, because I know that if we do it with someone else, they'll be like, oh, it's this, and then I'll bring it.
No, okay, because
But again,
I don't want to write this thing.
usually happens.
Just write it. Just sit down and write it. It'll take
Which means that it doesn't matter the whole thing.
It will probably finish.
Parent
It's the
value,
same
you
thing.
need to write
We did
it.
the same thing 3 times.
You can import
You can
from
write
there.
it once, and you have to say we repeated this with
Then
this
again,
data
it's
set
like
which shows this, we repeat this data set which shows this.
sector
Done.
cache is it's
You don't need to explain the whole
all
thing.
parts of the system.
That's what I'm going to say.
No, I'm gonna read your.
That's right.
You're gonna read what?
I'm gonna read your answer.
Okay.
And then you say.
Yeah, but I need to press renew.
Yeah, okay. Oh, okay.
My sister is coming Sunday. I'm gonna meet her. Well, I'm gonna tell her to come late on Sunday. That way.
Okay, let's get started. Now that I've figured out how to work with the gadgets here, I hope that will not change. Okay, I have one more point to make over here. But even if you have an RTL design that models everything, that's not the same thing as real design, because there's stuff that goes on in between the RTL and the real design. You lay it out. It turns out there is an error between these two things. Because you don't necessarily model everything in the RTL. Later, the circuit designer, the VLSI designer who does the design changes some stuff. That doesn't get propagated back into the RTL. So for example, even real chips, usually the low-level models, very, very low-level models like RTL, has error. And that error is about 1 to 3% or so in terms of performance. That's interesting. And people try to close that error gap if they want to do this loop back and fix the higher level models. And even RTL is not easy to fix. So that gives you the difficulty of even the higher level models. So higher level models, if you get 10% error, 15% error, that's good actually. Okay. We've discussed this. Is that coming from me? I'm using a different one, so maybe I'm not done with the issues with the gadgets here. Let's try to reduce the microphone volume and the system volume. That sounds better, right? Okay. Okay. I don't know what this is from. Okay. Let me tell you a little bit more about DRAM simulation. So this is a simulator that we have developed. But this is just an example. This is simple because our topic is DRAM. But this fills a gap because there wasn't a lot of simulation infrastructure in DRAM memories. And there's a paper that you can, again, read and review. That's a short paper. This is a short one. This is only 4 pages, as opposed to all of the 12-page papers that I've been keeping assigning you. But as you can see, there's a huge proliferation of the space in main memory today because it's important and because there are many, many design goals. There are a bunch of CPU simulators, which we're not going to talk about for now. And you're actually going to be working with some CPU simulators. And you're going to add support for caches in a later lab at a higher level simulator also. But there's less on memory simulators. And clearly, as we've discussed, the DRAM and memory control landscape is changing. And there are many new and upcoming standards. And if you look 20 years from now, it's not clear if you will see any of these standards over here, actually. And there are many new controller designs. And a fast and easy to extend simulator is very much needed, especially when things are changing this quickly, right? You have so many standards to explore. You want to figure out what are the different benefits and downsides of different options that you have in the memory interface. Again, you don't need to understand all of these. And they all have slight differences in terms of how they approach the memory interface. Well, maybe not so slight. For example, these are 3D stacked, right? They have very high bandwidth, low latency. But basically, the idea is what's to design a simulator that enables you to explore this design space very, very quickly so that you can hopefully make the right choices for whatever you're designing. So Ramulator it's actually the simulator that we had been using in my group since the times when I was at Microsoft Research. We developed it at that time in C# out of all languages because C# happened to be a nice, easy to develop language in Microsoft at that time. And then it got evolved over time, over the course of like 12 years or so at the moment. We actually released a C++ version. But basically, the idea is to provide out-of-the-box support for many DRAM standards, so you can find these. And it's actually much faster than the fastest open source simulator as well. And you can read the paper if you're interested in that. And the key is it's modular and extensible to different standards. So simulator design is an art itself also, right? We have not described, and we're not going to talk about that art that much. Like any other software that you engineer, there's some art associated with that engineering. And if you want to, you can make it more modular and extensible such that you can model many things much more simply. And also making it faster at the same time is important, right? So what kind of things that you can enable? So you can read the paper for more detail. I'm not going to go into detail. But basically, this is some sort of testing that you need to do to figure out how fast your simulator is. For example, in this case, we evaluate in terms of runtime for some workload, random workload, and streaming workload. As you can see, usually random workloads take much longer for different simulators as well because you need to do more in the memory controller to actually satisfy the needs of that random memory controller, random access workload, which is you get row conflicts, right? That's one example. Whereas streaming is you don't get row conflicts. And this is the request per second performance. That's another way of evaluating this sort of simulator. And this is memory consumption, right? How much memory do you need? That's another evaluation metric for a simulator. So simulator design itself is a design space, clearly. But what can a good simulator enable you to do? Things like this. This is just one example from the paper. Basically, you can take a bunch of workloads. In this case, the workloads are 22 workloads. I believe these are spec workloads. When we have time, we can perhaps talk about benchmarking. How do you benchmark the performance or some metric of a system? Spec is Standard Performance Evaluation Corporation that actually was formed for that purpose. And they developed a bunch of workloads to benchmark computer system performance. And this is their CPU workloads. And basically, across 22 workloads, you can run a simulation that looks at performance. This is IPC, instructions per cycle, of different DRAM. So you have the same processor. You attach different DRAM to it. And you look at the performance impact of different DRAM. So the baseline is DDR3. So, for example, in this case, using DDR4 instead of DDR3 improves performance. That blue part happens to be 14% more. And this is the distribution across the workloads. Right? You can actually see the distribution over here and where the distribution is heavy, as you can see with these graphs. There was a name for these graphs that escaped me right now. Does anybody know? Box plot. But there was a specific name for these things. Yeah, it is a form of.
Violin plot.
See?
Violin plot, like that.
Widen?
Violin.
Yeah, something like that. I don't remember though. Oh, violin plot. That's right. That's right. Yes, this is a violin plot. It's not a box plot. You're right. Well, you could consider it a compressed box plot, but it's a violin plot. Yeah. It usually looks like a violin. Yes. Thank you. You get bonus points. I'm not sure if I can give you a violin, but do you play the violin? Okay. Then I don't have to give you a violin. Although usually giving something to someone enables them to do it, but that's okay. This is a violin plot. That's right. So basically, this simulator, because of its flexibility and speed, enabled us to figure out that DDR4 improves performance by this much. Again, accuracy I'm not commenting on at the moment, because it's not a function of just the simulator, but also the CPU model, right? The accuracy. So the simulator itself is modeling the memory controller as well as the DRAM itself, but it can attach to some other CPU simulator so that you can actually get performance results that look like this, right? It could attach to actually much bigger, various different CPU simulators at varying levels of fidelity. And you can read the paper for that detail. But also, you can actually now compare different DRAM standards. For example, LPDDR3 reduces performance by 12% compared to DDR3. Why? You can guess, right? LPDDR3 has longer timings. Yeah, even though bandwidth is the same, latencies are longer compared to DDR3, right? And LPDDR4 is slightly better than LPDDR3, but its variance is higher for some reason, right? Now you can go and analyze why that's the case, assuming this is not an error. But clearly, you can guess some trends. For example, sub-array level parallelism is better than DDR4 in this case, GDDR5. And you can see that HBM, high bandwidth memory, actually is the best in this case. It provides you, on average, 27% higher performance. And the variance, there are some applications that gain a lot because they're probably bandwidth bound in this case, right? And you can guess that. So you can see the bandwidth, the peak bandwidth of different memories that are listed over here. So that's the beauty of high-level simulation. You can do studies like this without having to implement any of these in your system. And remember, implementing this is really hard, right? If you have a real system that supports all of this, well, good luck. You'll probably design it 30 years later or something like that. In fact, I know people who design just DDR3 controllers, and they've spent years designing DDR3 controllers, just that particular thing, because making it work takes a lot of time. And this is DDR3 multiplied by 10, probably. OK, so that's the beauty of simulation. And you can read the paper. You can actually download it. This is actually being used a lot in industry and academia, and we need to update it actually more. But this is the extra credit assignment. You can review the paper. It's only 4 pages. And you can download it and run and see for yourself, basically. Compare the performance for whatever benchmark. And I picked libquantum over here, but you can actually find other benchmarks as well. And you can upload your report to Moodle. So feel free to do these extra credit assignments if you want extra credit, or if you want to do it just for fun, right? Maybe you can think while you're sleeping tonight, oh, I heard about RAM later. I'm going to run after I wake up. You could do that, right? OK. OK, let's talk about memory latency. Let's see if we have enough time to do justice to it. I think we do. Maybe not full justice, but at least some justice. OK, remember latency? Well, I think maybe I'll do some justice to something else before the latency. So I'll give you another view of the DRAM, because this gives you what the design is currently in terms of latency. So this is a real chip as opposed to my other picture. And these are slides from one of my students who graduated recently, Vivek Seshadri. But when you're designing a chip, you have many goals. And we're going to focus more on latency. But clearly, there are really tight connections between all of these goals, especially cost and latency. Cost is also capacity. They have a clear trade-off, which we're going to talk about. But let's look at this chip a little bit more, just to make this more real. So if you look at a chip, if you look at a bank, so these are actually 8 banks, 1, 2, 3, 4, 5, 6, 7, 8. And you have some logic in between, row logic. You can see the row decoder over here. You can see the bank I/O logic. And even a bank itself is actually not a single monolithic thing, as I said. It actually has multiple of these things. And this is Vivek's pictorial way of depicting it. It actually has many more of these subarrays, what are called subarrays. So let's start with the sense amplifier. I'll start again at the bottom. So basically, sense amplifier has two inverters, cross-coupled. This is hopefully clear. It's actually an SRAM cell, the way you look at it. And it has an enable logic over here. When you enable it, it basically has two possible states. Either this part is VDD or this part is VDD. And you connect either part to a bit line. So assume that this is larger than this slightly, higher than the sense amplifier threshold. This is disabled sense amplifier. When you enable it, it basically senses this difference. And basically, because of the feedback, amplifies this to VDD and amplifies this part to 0. Right? That's how it works. So on the other hand, DRAM cell is capacitor-based. You have an empty state, logical 0, let's say. You have a fully charged state, logical 1, let's say. The DRAM cell is very small. It cannot drive circuits. And in fact, the sense amplifier that I'm going to show, and it's not going to be to scale, the size of this today is more than 100 times the size of each of these DRAM cells. Because this needs to drive stuff, whereas this doesn't need to drive much. And this also needs to be small so that you can have more capacity, right? That's the idea. OK. And reading destroys the state because it's capacitor-based. So let's look at the capacitor sense amplifier interaction. Basically, you can either have a cell that's not charged that will be connected to the sense amplifier. Eventually, you want to get this in the sense amplifier. You want to sense that it's 0. And you have a cell that's charged. You want to sense that it's VDD. How do you do that? Basically, you connect, by an activate command, you connect the capacitor to the bit line. And the bit line is pre-charged to begin with. It's 1.5 VDD on both ends. And the sense amplifier is disabled. That's why it can keep the 1.5 VDD over here. So that's not a perfect SRAM, if you will. It's really a sense amplifier because you can enable and disable it. And when you connect the cell, you basically share the charge of the cell with the bit line, which means that you perturb the bit line slightly because this is very, very little charge over here. And once you perturb the bit line slightly, when you enable the sense amplifier, you get VDD over here. That's how you sense. Right? And then the sense amplifier actually starts driving because it amplifies it, and then you restore the data in the cell. That's exactly how the low-level stuff works. So this is the building block, basically. Building block is really the sense amplifier and the cell, but you have many, many cells in a bit line. And you have many, many cells in a word line also. And this is actually what's called a subarray. And then you have a single row of sense amplifiers so that when you activate an entire row, you can sense the entire row also. And this is what a subarray usually looks like today. You basically have a row decoder that figures out which word line, and then you have the sense amplifiers, array of sense amplifiers here. And this is one value that you can have over here. Make sense? And this is not a single bank. This is just part of the bank right now. And how many? OK, yeah, let me go over here. So now we're going to construct a bank. A bank consists of multiple of these subarrays, not two. In today's system, that's 64. Could be 128. Again, it's a design choice. Right? And the data that you get out of this bank is actually 64 bits. That's the data out that you have over here. So clearly, you enable a row of sense amplifiers. It's 8 kilobits, and you need to get the data out. How do you get that data out? Well, that data out, there's some other interconnect that I didn't show you over here. Those are called the global bit lines that are actually much larger. And because they're much larger, they're larger because they need to drive data across the chip, if you will, or across a large part of the chip. As a result, they need to be larger. And as a result, you cannot have many of them. That's why it's only 64 bits or whatever again. So when you supply the address, OK. Yeah, and then you also need to have address connections clearly over here. So basically, a DRAM chip consists of many of these. Again, this is not to scale because it's not just 2. It could be 32 over here, right? For each bank, you can have 32 subarrays. And this is how the bank I/O fits in. And they have a shared internal bus. That's how you get the data out, basically. Right? The 8 bits that we've discussed out of the chip, Maybe you fetch 64 bits, that's right. That gets buffered somewhere, but then you get 8 bits at a time because you don't want many, many pins in the chip, as we've discussed before also. So let's look at the operation from this perspective. Basically, when you activate a row, let's assume that that's what we want. That's the 8 bits we want in this case. When you activate a row, you supply the row address, and one subarray gets activated. In this case, this subarray, the row address happens to activate this word line, and that word line gets buffered. The values of those word line gets buffered in the row buffer. Right? And then you need to send the read and write command to the column, which means that you supply the column address, and you get the data out into the bank I/O. Right? That's how it works. And if you want to pre-charge things, you basically send a pre-charge command, and that deactivates the particular subarray over here. Essentially, you have many, many rows of sense amplifiers here, as you can see. Right? The abstraction that we had in a bank is different right now. Right? We went one more level down. And the reason is you cannot have those local bit lines long because that's expensive and also high latency. But even this is high latency, actually. Now we've chopped up a bank into, in this case, 2, but really 32 subarrays. But even this is high latency for multiple reasons. One is the subarray access latency, the sensing latency, and actually that tends to be the dominant. But then there's also the latency to drive the signals out of the bank. So we're going to talk more about that. And you remember this slide. I don't know if you remember the numbers, but capacity has improved a lot in the past. Bandwidth has improved still a lot, but latency is improving slowly, right, 30%. So we're going to talk about latency because, as we discussed, it's important. Many workloads actually suffer from it. And these are some papers, again, you can read, which we may actually talk about later on. This is a good paper from Google that talks about their data center workloads. So we're going to concern ourselves with the long DRAM latency in this lecture and hopefully some part of the next lecture, maybe not all. And we're going to talk about why we have the long latency. So hopefully we'll cover the first reason in the next 10 minutes. But there are 2 major reasons. Actually, you could, if you come up with another reason, that's good. That's actually research. Maybe you can come up with some other reason that's more researchy over here. But I'll give you 2 known and relatively well-studied reasons over here. The first is due to the design of the DRAM microarchitecture. This is a conscious choice, basically. The goal has been to maximize capacity per area, not to minimize latency. Of course, this is wrong, what I said directly, but because clearly this design that I showed you is trying to minimize latency. That's why we have subarrays inside a bank, right? But even that's not enough. Still, the overwhelming goal is to maximize capacity. And the second reason is also very interesting. There's remember the timing parameters that I showed you earlier? Even those are conservative. They're really designed for the worst case scenarios. So perhaps we can relax that worst case. And I'll show you examples of this. But let's look at the first one. What causes the long latency? This is, again, a pictorial view of what you've seen earlier. If you look at a DRAM bank, let's say, you have the cell array. And it's really divided into these subarrays. And you have the subarray access latency and the I/O access latency after that. And you can, at a high level, say DRAM latency, subarray latency plus I/O latency. And this turns out to be dominant. OK, why is this so slow? Again, the answer is interconnect, as we've answered before. Basically, this is what a subarray looks like. You have the cells. And as I said, the sense amplifier is more than 100 times the size of a cell, because it has a different function. And we want the cells to be as small as possible to maximize capacity. So we have a large sense amplifier. And today's designs want to amortize the sense amplifier cost. So for example, you can have 1 sense amplifier per a row of cell. That's not good for capacity, right? Then you have a lot of sense amplifiers. But today's designs string together many cells to be sensed by the same sense amplifier. 512 cells, 1,024 cells. This is good because it gives you small area. It amortizes sense amplifier cost. But this is bad for latency because as you string together more stuff, as you make the interconnect longer, you have large bit line capacitance, large capacitance on that bit line. So you have high latency as well as high power. Long interconnect is not good for power either. OK, so there's a very clear trade-off that happens in DRAM and actually in many, many memories that are bound by interconnect. You can have a long bit line architecture that looks like this, few sense amplifiers, but a lot of stuff attached to it. You can make it faster by chopping into smaller subarrays, let's say. In this case, you have a short bit line architecture, many, many amplifiers, and this is not to scale because the size of this red part is 100 times the size of this one of these circles, right? It actually becomes much worse. You can, of course, make this smaller. As a result, you get higher latency. So there's a clear trade-off between area and latency. You can get lower latency by increasing the capacity. That's not the trade-off that's made in DRAM designs today, because that comes at a high cost, because now you're actually having a much smaller chip, right, in the same area. So let's look at this trade-off. Basically, this is latency. This is normalized DRAM area, normalized to this point over here. And that, ideally, you would like to be here, cheaper and faster at the same time. But you get a Pareto optimal curve that looks like this, depending on what you're optimizing for. Commodity DRAM makes the trade-off over here at this extreme case. You have long bit lines. But if you actually reduce the size of number of cells that are connected in a bit line, if you have only 32, you can have much lower latency, as you can see over here, right? But then your DRAM area increases significantly, as you can see also. So your cost increases. So there's clear trade-offs. There's some fancy DRAM that you can buy today if you pay an arm and a leg, called reduced latency DRAM, for example. They make the trade-off over here. And as a result, partially as a result of that, they are much higher cost. But they're lower latency. These are actually used in specialized routers, for example. When you're bound by memory latency, you can buy that reduced latency DRAM. And I believe those routers are one of the major customers of this reduced latency DRAM. They're not manufactured as mass as commodity DRAM because they don't have many customers, and they're also expensive to begin with, right? And that's a chicken and the egg problem, right? If you're expensive, you'll naturally have fewer customers, unless you market well. OK, so the goal is really somewhere here, ideally, right? And if you actually come up with something in DRAM that clearly brings this Pareto optimal curve over here, that's definitely a big contribution. Or that could also be magic. I don't know. But let's see how we can optimize it. So whenever you have a trade-off that looks like this, if you want to get at least some of the best of both worlds, you should always think heterogeneity. That's a very general principle. You can design something heterogeneous that tries to approximate the best of both worlds. And that's the idea of what I'm going to describe. And this is one of your readings. Part of it is required, part of it is not required, but you can always review it. So clearly, we have a trade-off. Long bit line is small area, but high latency. Short bit line is low latency and large area. You can see greens and reds. And whenever you have this, you can think about, oh, maybe I can try to get the small area of this while getting some of the low latency of this. And that's the idea over here. You start with this long bit line architecture, but you create a portion of it that looks like short bit line by adding isolation transistors in between on the bit lines. The idea is you don't have a perfect bit line, but you can actually turn off part of the bit line. If you turn off this part of the bit line by disconnecting the top portion from the bottom portion by isolating it, now this part looks like this, right? The sense amplifier sees only a short bit line. And that's the idea over here. And I want to discuss this idea because that changes the trade-offs a little bit. So that's called tiered latency DRAM. You get small area using the long bit line. If you want to access something over here, you need to turn on the isolation transistor and get high capacity and access over there. But if you want low latency, you can put the data that requires low latency over there and turn off the isolation transistor and access it this fast. That's the idea. So let's take a look at the evaluation of the latency. Of course, there's a design space here also. Commodity DRAM, you have 512 cells per bit line. If you have a tiered latency DRAM that looked like what I discussed earlier, so this is called the near segment, and this is called the far segment. Near to the sense amplifier, and it's fast as a result. Far from the sense amplifier, it's slow as a result. So if you have a near segment that's 32 rows and far segment that's 480 rows, I'll show you some results. And how you do this evaluation is another question, right? Basically, these are some SPICE simulations. You can see this in the paper. And you need some power and area evaluation to understand this as well. So basically, I'll give you the takeaways. Near segment latency reduces by about 56%. This is wrong. This should be actually somewhere over here. That's actually 56. This should be 44. The far segment latency actually increases by 23%. So you have a trade-off now, right? Compared to commodity DRAM where you have 512. cells. The trade-off, which means that accessing data that's in the far segment actually is much slower now. But you gain power. If you keep data in the near segment, you gain power also. The power reduction is about 50% over here, but then the power increases in the far segment. The reason is, whenever you enable the isolation transistor, you have additional resistance in the bit line. That's why both power increases and both your latency increases. And it turns out DRAM area overhead is about 3%. So 3% is not terrible, but not that great also. But again, you cannot get something without paying for something. So let's take a look at where this trade-off is now. So our goal was this. The near segment provides us this, but far segment takes us back, which means that now you have a heterogeneous memory that you need to manage somehow. Again, you can imagine many potential ways of managing it, hardware or software, right? I'll go through very quickly. You can have a hardware-managed inclusive cache. You can read the paper for details. Hardware-managed exclusive cache. Exclusive versus inclusive. Inclusive in this case means the data that you cache is also in the far segment. That's inclusive. If it's exclusive, you swap the rows between the far segment and the near segment. That way, you don't lose capacity. Whereas if you're inclusive, you lose capacity, right? That's really a cache. Or you can figure out what are the frequently used pages and map the pages to the near segment. Map the frequently used pages or latency critical pages to the near segment. Now, this doesn't seem to work very well. Simply replacing DRAM with TL-DRAM and not doing anything doesn't seem to work well because frequently used pages don't magically get mapped to that near segment in existing systems, at least. So I'll give you some results. Basically, if you have a near segment as a hardware-managed cache, this looks like this. You have, in a bank at least, or in a subarray, you have this far segment, you have this near segment. Far segment is really your main memory, and near segment is some level of cache, very close to DRAM, inside DRAM, actually. There are two key questions. Whenever you access the data from far segment, and let's say you want to cache it, how do you efficiently move the data from here to here? And the second question is, how do you efficiently manage the cache? What do you decide to cache in this near segment? Clearly, you're caching rows of memory, right? Let's take a look at the first one. So if you want to cache some row from the far segment to near segment, one way of doing that is through the memory controller. Bad idea, because this is inside DRAM, right? You don't want to go through the memory controller, read the entire row, and write it back to the same subarray, because these are actually already connected. So the idea is, we're going to look at this later on. Source and destination cells share the bit lines, if you look over here. If you actually connect the source to the destination directly, almost directly, you could enable a very high bandwidth copying mechanism inside the subarray. I'll finish in a couple of minutes, almost. Basically, that's the idea. Transfer from the source to destination across the shared bit lines concurrently. How do you do that? Let me give you the idea. You activate the source row, which brings the source data. Of course, the isolation transistors are enabled here, which brings the source data into the sense amplifiers. That's the first step. And the next step is you activate the destination row to connect the sense amplifiers to this, basically. With these two steps, you can do the copying. Of course, you need to turn off this one when you're activating. So basically, you activate the source row, which brings the data over here. And then you disconnect the isolation transistors. And then you activate the destination row, which brings the data over here. Right? Makes sense. That's simple. That's copying. And that's very quick. So how do you efficiently manage the cache? I'm not going to discuss this. Actually, you could, again, this is a cache. And you could employ other cache management policies that we've discussed before. But I'm going to give you results with using this as an LRU cache. Very simple, least recently used management. And I'm not going to go into the even detail. So if you have a substrate like this, if you use it as an LRU cache, it turns out, even with the dumbest cache policy, basically, every time, whenever you access a row, you bring the data into the near segment and then cache it. That may not be the best policy at this level. Remember, we're very close to DRAM. You've already gone through 4 levels or however many levels of caching. Right? This is even after the row buffer, if you will. OK, so even with that policy, you see significant performance gains. It's more than 10% average across a number of workloads. I believe this is about 80 workloads. And getting average that more than 10% is not that easy, actually, across a very large number of workloads. And power benefits are even higher, actually. You can see that the power reduction is about 20%. OK, and I'll give you one more to see the trade-off. Basically, nobody said that you have to have 32 rows as your near segment length. You can vary that. And in simulation, again, you can study. So this is, you can look at the paper for the simulation, but this is really simulation with a tool that looks like Ramulator, again. But you could, with Ramulator, you can actually change the near segment length and study the trade-off. The trade-off is, as you increase the near segment length, you have larger cache capacity, but you also have higher cache access latency. Right? And it turns out the maximum IPC improvement happens at 32 rows in the near segment. OK, so you can read the paper for more detail, and you can review it for extra credit. But there are a couple of sections in this paper that are required so that you understand the DRAM latencies very well. Well, if you've gotten it in the lecture, that's perfectly fine. Maybe you don't need to read the sections also. OK, that's all I have. Any burning questions? OK, then I'll see you tomorrow. We'll pick up here.